scared shitless.
So you can like spread it out, so you don't have to fumble with things.
Sorry. Thought I was on this PDF here. PDF, right? Okay, yeah, I think it was. So you're St. John's?
We have a clicker too.
We'll give you one.
Thank you.
Yeah. Just like
Yeah, just run them out.
Oh, yeah. Oh, that works. Thank you. We're just waiting on one judge, so hang tight. We'll get started in a minute. Okay, I think we can get started. So welcome, St. John's School, your first presentation. You're welcome to begin when you're ready. Before you do, please introduce yourselves and just give us your names and what year you all are. And then you have 15 minutes.
Okay, thank you. My name is Helen Yang.
I'm Jack Vu. I'm a senior. I'm David Chin. I'm a junior.
Anik Banerjee. Anik Banerjee. I'm a junior.
And I'm Brandon Wu. I'm also a junior.
I'm a junior as well. And we're team 17524 from St. John's School. As Texans, we're no strangers to the heat. In this year's M3 challenge, we explored how extreme heat affects both individuals and infrastructure, from modeling how homes heat up without air conditioning, to forecasting long-term energy demand, and finally, to identifying which communities in Memphis are most vulnerable to these growing risks. To start off, in question 1, we were tasked with modeling the temperature inside 4 distinct homes experiencing a heat wave over a 24-hour period. Our first major assumption is that the house is modeled as an object with a uniform internal temperature. This assumption is essential for applying Newton's law of cooling, which relates the rate of heat transfer of an object to its temperature difference with the environment. Second, internal heat is assumed to come mainly from occupants and electronics. In typical residential settings, the main sources of internal heat are from occupants and electronics. Third, conduction through walls is assumed to be proportional to the surface area of the walls through which heat is exchanged. Fourth, additional heat transfer between indoors and outdoors occurs through ventilation, such as airflow through cracks. And finally, solar radiation is considered an external heat source that adds energy directly to the interior of a home, accounting for heat from sunlight entering through windows. In developing our model, we initially considered two approaches. One, a physics-based differential equation model, or two, a time series model. Our differential equation model is based on Newton's law of cooling, which relates an object's temperature change to its environment. Fundamentally, this closely mirrors how houses absorb or lose heat from their surroundings. On the other hand, a time series model predicts future indoor temperatures by identifying patterns in historical data, making it useful for capturing trends without directly accounting for physical factors. We concluded that a physics-based model is best suited for a problem statement because it, one, doesn't require dwelling-specific historical data, which was not provided and would be nearly impossible to find, and two, can be easily generalized to different house types due to having flexible parameters. The next step in building our model was considering each individual factor and their relationship to temperature change over time. The four factors we considered were conduction, radiation, ventilation, and internal heat generation. As you can see in our equation, both conduction and ventilation are proportional to the difference in internal and external temperature, consistent with Newton's law of cooling. The other two factors are related to direct energy inputs, where radiation is modeled as a term based on solar intensity and the absorption properties of the house, and internal heat generation is based on the assumed wattage produced by occupants and appliances. To solve the differential equation we derived, we outsourced data from the ASHRAE Engineering Handbook on coefficients associated with the four factors we mentioned, as they vary between different housing types. Next, to implement this model, we wrote a Python script that used Euler's method to numerically approximate the solution to the differential equation, giving us the final temperatures for the four dwellings over the 24-hour period.
Now for the results. We found that, regardless of factors like home insulation, size, and height, each of the four sample dwellings reached dangerously high temperatures, with peak temperatures all around 100 degrees. These findings imply that, regardless of a home situation, a lack of air conditioning yields potentially dangerous results for that home's inhabitants. For the sensitivity analysis, we perturbed each of the model's coefficients, as well as the home's initial temperature, by 10% in both directions from their original values. We then computed and plotted the total range of outcomes for these altered conditions. We found that the maximum and end temperatures for this entire range of possible curves varied less than 1 total degree, proving this model's strong resilience to changes in initial conditions. Some strengths of our model were that it captured the most significant physical factors in a home's temperature change, and that, as shown in the sensitivity analysis, the model proved resilient to changes in initial conditions. A weakness, though, is that it treats the model the model treats the home as a single homogeneous thermal zone instead of considering internal temperature variation, for example, warm or higher stories. The model may also struggle with extreme deviations due to weather changes like humidity, cloud cover, or excess wind.
On to section 2. Sorry. In part 2, we were tasked with developing a model for peak demand of power in Memphis and using it to make forecasts up to 20 years in the future. Our first step was to find relevant data on both temperature history and economic growth, and new data was collected and 7 new predictors were defined. Most importantly, we defined peak demand as the highest hour of consumption in megawatts each year. As you can see, we have a data table of that peak consumption here. For our model, we need a few key assumptions, the most important of which is that historical trends remain relatively similar. This assumption allows us to generate plausible future values for our contributing features. The remaining assumptions are all important to making a robust and accurate regression model. Our next step was using the data to create a model. We discussed using a logistic regression, linear regression, and time series models as potential candidates for the problem. The nature of the problem did not suggest any justifiable reason for a carrying capacity, discouraging a logistic type model. While time series models can be effective for capturing seasonality, they require fairly serious, dense, and a regularly spaced historical data. Ultimately, we chose to use a more robust and interpretable model in a least squares linear regression. In our next step, we selected our model predictors through a process of backward selection, removing the most statistically insignificant components in each iteration of the model. This process narrowed our list of potential predictors from 7 to the following 3 possibilities: peak temperature, GDP, and dollars invested in the power grid. We found, though, according to our heat map of correlation, that GDP and dollars invested are highly correlated. And to avoid overcounting for similar phenomena, we removed the less predictive factor in dollars invested. As such, the final 2 predictors were peak temperature and GDP. Under the assumption that these 2 predictors change linearly for the next 20 years in line with historical data, we recorded 20 years of possible future values for these predictors. We then plugged these predicted values into the regression model to forecast that in 20 years, Memphis may need support for 3,357 megawatts of power at its peak in 1 hour. To confirm the validity of our model, we back-tested the model on data from 2012 to 2022, and we analyzed our residuals. The mean squared percent error between the actual peak load and our model's predicted peak load in those years was just around 1.94%, indicating an accurate model. Our residual plot shows no discernible pattern and a constant spread, thus showing that the errors are fairly random, and this linear regression model captures the relationship well. Our regression model provides transparent methods and interpretable results and avoids collinearity. The low error and strong residual results also indicate a robust model. However, some weaknesses may be sensitivity to outliers and the assumption of linearity or possibly nonlinear solution, or possibly nonlinear relationship.
For our next challenge, can you hear me? For our next challenge, we developed a vulnerability score to help the city of Memphis equitably allocate its resources during events of extreme heat. In designing a model to assign vulnerability scores, we made the following assumptions. Firstly, all Memphians behave rationally. During heat waves, they will act to protect their health and well-being. Second, min-max normalization is valid for the given data. We dealt with various metrics with different units, and in order to combine them into a meaningful vulnerability score, they must be normalized, scaling from 0 to 1. We assumed that there would not be any significant outliers, and because min-max scaling is a linear transformation, it would preserve any existing skewing of the metrics. We also assumed that each factor, once scaled in the same manner, would affect our vulnerability score equally. Each factor represents a unique quality of the community within a given neighborhood, and assigning them equal weights ensures that no one factor would overshadow another. Finally, we assumed that zip code is representative of a neighborhood. These are well-defined administrative units that allow for meaningful comparisons across the city. We considered a variety of potential factors that affected vulnerability, but as shown in our heat map, many of these factors were correlated with one another. For example, population and the number of households. So we made sure to avoid collinearity between the factors used. Eventually, 4 factors were chosen as representative of the vulnerability of a community. These are we had an animation here, but these are economic standing, which determines a community's access to air conditioning, green spaces, and healthcare. We also considered that a neighborhood with a higher population would have more people at risk, and these people will put more strain on the power grid. Furthermore, we considered that the elderly tend to spend more time at home, which further strains the power grid, and they may have underlying health conditions that are worsened by extreme heat conditions. And finally, we considered mode share. So people who get to work by walking or public transit will have their commute more drastically affected by heat waves due to the limited availability of shade and water. So for our model, we chose to use a direct sum, normalizing each of our 4 chosen factors, and then combining them into one total score. In the absence of any ground truth outcomes, which provide a reference for measured impact, this index instead reflects a synthesis of the key risk factors.
Here are the results of our scoring. When we look at the bar graph of vulnerability scores by zip code, we can see a wide spread. Some communities are relatively resilient, while others are far more vulnerable to the impacts of extreme heat. Our results can also be visualized on a map, which makes it more clear where the most vulnerable areas of Memphis are located geographically. The darker regions are those with a greater correlated vulnerability score. In South Memphis, which was the most vulnerable area according to our analysis, we see a rapidly growing population, yet a significant share of residents live below the poverty line. In the event of a heat wave, many of these residents would likely struggle to adequately respond. Downtown Memphis brings large numbers of people from diverse backgrounds together every day to support the city's economy. However, these busy areas would become serious points of vulnerability during heat waves, with crowds exposed to dangerous conditions. At the medical center, this vulnerability is similarly severe. A high concentration of individuals that require specialized medical care makes this area particularly susceptible to the impacts caused by power outages and heat waves, outages which could prove to be life-threatening. Our model compiled well-justified features with realistic implications of vulnerability, resulting in an interpretable and reasonable model. Furthermore, our chosen factors were found to be independent and correlated, meaning that direct summation within our model was both meaningful and interpretable. However, it is important to note that the model is built off of factors that are not direct measurements of heat wave consequences. Rather, we selected factors that we believed would influence the consequences of heat waves. This unsupervised model could benefit from real consequence-based data to ensure reliability. However, this data would prove to be difficult to obtain in real life due to many restrictions on data surrounding health outcomes. HIPAA is an example of this. With these findings in mind, our group recommends that the city of Memphis implement a Cool Neighborhoods initiative to alleviate the impacts that heat has on Memphis communities. This program would target vulnerable communities, upgrading their streets and sidewalks with reflective, heat-reducing pavement and increasing shade with trees and bus shelters. These improvements would lower street-level temperatures, make walking and waiting for infrequent buses more comfortable, and lessen reliance on air conditioning, especially for seniors. So as we showed in part 1, the loss of air conditioning due to power outages forces people to endure life-threatening temperatures inside their own homes. At the same time, peak energy demand across Memphis will only continue to rise in the coming years, placing further strain on existing infrastructure. Yet these impacts are not felt equally. Vulnerable communities like those you've identified bear the brunt of the consequences, facing greater health risks and economic challenges. That's why we are proud to propose our policy solution to the city of Memphis: targeted infrastructure improvements that offer a meaningful path forward to protect its most vulnerable citizens. Thank you for your attention. We now stand open to questions.
Thanks for the presentation. I can start with a question. So I'm curious about the part 2 model. You do this linear regression, and I wanted to better understand what the data looked like that you fed into that model. So you mentioned something like investment into the power grid. What data did you use? Where did you collect it? And maybe like tell me a little bit about it.
Yeah, sorry. So we got most of our data from MLGW, like the Memphis, I think, power supplier. And we had a lot of different factors that we considered. I think I said 7. And our final few were GDP and peak temperature. However, other ones that we did consider and had found data for were dollars invested into the power grid, and even things like number of EVs used, and just a lot of different economic and temperature factor or temperature data that we had found online.
So
them.
it's like by a year or something, or how do they produce?
Yeah,
this?
all by a year.
And then how far back did you have it for?
Yeah, I think most of our data went back to 2007, although we only used from 2012 to 2022 in our model because that was like the data that we had for every single factor.
Okay, thanks. It's like it's a cool model that it uses so many features. It's a relatively brief time span, right? 2012 to 2002.
Yeah.
So do you think that impacted maybe the results of the model at all? Or how could we, given more time, how could we account for that?
I think. Do you have something to say?
Sure. Yeah, and I think that is one of the big challenges of this competition, right? Finding enough data to use reliably. And I think that's why we decided on a linear regression, because of its robust nature and just very high amount of interpretability. So in light of limited data like we experience here, I think that modeling after linear regression is a really safe option. And that's why we're really proud of our Part 2 model.
Yeah, great. Thank you.
All right. Can you hear me? Okay. Am I? All right, good. First, I do want to compliment your choice, in question 2, between multivariate regression and time series. That was interesting. My question is, though, about question 1. So in your sensitivity analysis, you varied starting coefficients. What are those starting coefficients?
Sure. So we had various conducting coefficients for different insulation types. And so, we pulled those coefficients from a handbook. And they're, we were fairly sure that they're reliable, but, insulation deteriorates, things happen. And so we were like, okay, if we change this coefficient as well as like our solar radiation coefficient, for example, which measured, right, how much heating there was due to the sun, as well as the ventilation coefficient. So like, how much do the windows, the cracks in the doors contribute? We had one more coefficient. What was it? It was the like the energy emitted from humans, right? Those were our 4 coefficients. So we changed those in either direction to see how these small changes in factors that aren't quite concrete would change the outcome. If that makes sense.
Thank you. Another question: why there was more variation in your results for smaller time than for the final time when you did sensitivity analysis?
I think just based on the trajectory, the conductivity sort of dominated the change in temperature throughout the day. And so as a result of that, the other 3 factors kind of became less relevant over the course of the day. And then you can see, if we pull up the slide, the trajectory kind of converges on just regression towards the outdoor temperature. And so that's why I think the difference gets smaller over time.
Thank you.
Thank you. I had a question about question 1 as well. You set up your differential equation, and then you said you used a Python script with Euler's method. Could you comment on how you chose your time step and how much faith we can put in that, or how you test how robust that is?
Right. So I think we just obviously there's some form of error associated with Euler's method and numerical approximations to solutions like this. But we chose a sufficiently small time step. I think it was, what was our time step? In the order of like a few seconds. So we just worked with the assumption that sufficiently small time steps would yield a solution that's fairly similar, which is, I think, fairly plausible for this situation. Thank you.
Okay, we have to wrap there, but thank you so much for the presentation. If one of your representative wants to get up and say, acknowledge anyone, this would be the time to do it, and then we'll transition to the next team. Thanks, guys.
So there are a number of people that our team would like to thank for this wonderful opportunity. First off, we want to thank our coach, Dr. Ralston. He couldn't make it here today to watch us, but I hope he's watching from home. I also really appreciated our chaperones, Mr. Gao and Ms. Fogler. They were both them and the coach worked with us throughout the entire last few months to prepare, and they've helped us so much with the whole presentation and make sure we can make it as great as possible. And I would also like to thank the parents as well for supporting all of us throughout the entire process, particularly David's parents, who gave us a place to practice and host our meetings. And I would also like to thank our school, St. John's. I think that they prepared us excellently to tackle this problem and learn the math that we needed. And finally, I want to thank MathWorks and the M3 Challenge because they provide our team with such an unforgettable experience and really allowing us to put our math skills to the test. We can't wait to participate in this challenge next year. Thank you.
Testing, testing.
Okay. Welcome Mason High School. They're gonna stand now instead of sit? Okay, you're all gonna stand because otherwise we couldn't see the slides. So you have 15 minutes to present. I'm gonna give you a 5-minute warning, a 2-minute warning, and a 1-minute warning. I'm just a bit hard to see over here because you're gonna want to look out to the audience, but I'll make sure you guys see the cues. Yeah, and then after that, we'll ask you about 5 minutes of questions and you'll have some time to thank whoever you want to thank. So whenever you're ready, go ahead and get started.
Hi, my name is Minja Zhang.
My name is Anish Iyer. My name is Raymond.
And my name is Ramya.
And my name is Vivian, and we are team 18111, representing William Mason High School from Mason, Ohio. Today, we will be presenting our solution to hot button issue, staying cool as the world heats up for our chosen city of Memphis, Tennessee. Last summer in Memphis, a mother had to move her daughter's oxygen tank into the car because the air inside their home was too hot, too dangerous to breathe. This isn't a future issue. It's happening now to neighborhoods that aren't equipped to handle the heat. Elderly die, and workers die while on the clock, and the elderly suffocate in their homes, and children aren't able to live their lives. The need to act isn't merely academic, it's deeply human. Now, Minja will begin with Model 1. Hot to go.
The dangerous reality of heat waves is a constant for populations without access to air conditioning in summer months. In the first problem, we aim to model the indoor temperature of a non-air conditioned dwelling in Memphis over a 24-hour heat wave day. Our key assumptions for this problem may be condensed into the following 2 points. First, we assume that residents follow all recommended heat mitigation practices. And next, we make some assumptions for model simplicity. Dwellings have square floor plans with 10-foot tall stories and have a uniform internal temperature. In developing our model, we hypothesize that changes in indoor temperature result primarily from 2 factors: solar radiation and heat transfer through the walls of the home. In order to account for the time-based nature of these factors, as well as the fact that heat transfer itself may be expressed as a differential equation, We utilize a differential model to relate indoor temperature to time-varying functions of external temperature and solar irradiance. Shown here is our starting differential equation. Inside the parentheses is the rate of energy transfer through the home, composed of components Q rad, or solar radiation, and Q flow, or heat conduction through the walls of the home. This is divided by the heat capacity of the home, defined as the amount of thermal energy required to raise the temperature of the dwelling by 1 degree Celsius. And by dimensional analysis, this equation yields us the rate of indoor temperature change. To first model solar radiation entering the dwelling, we take the global horizontal irradiance, which is defined as the amount of sunlight hitting a horizontal surface at any given point in time, and we apply 2 coefficients to it in order to account for solar radiation blocked from entering the home. R sub S represents blocking by shade around the house, while R sub W represents blocking by walls around the house. Next, in order to model heat conduction through the walls of the home, we apply a modified form of Fourier's law, which expresses the dependence of heat conduction rate across a surface, in this case a wall, on the difference in temperature between the 2 surfaces of the wall. In lieu of traditional parameters of thermal conductivity and wall thickness, we utilize a construction industry standard of R value, directly proportional to the insulatory capacity of a wall. Notably, in order to account for the warming of outside surfaces due to solar radiation absorption, we add a factor of 50 degrees Celsius to the ambient external temperature in order to obtain the surface of the temperature of the outside surface of the home. We then determine the heat capacity of the home based on the volume of air in the dwelling and existing physical parameters. Finally, after calculating the total surface area of the walls in the home and substituting all of our prior expressions into our initial equation, we obtain our final model. It is dependent on 2 time-varying functions, external temperature and global horizontal irradiance. All other parameters are constants found through either literature review or provided in the M3 dataset. Next, Anish will explain the results of our first model.
We collected hourly temperature and global horizontal irradiance data based on 4 different past heat wave events in Memphis. We then used Python to optimize time-based regression inputs for our model. We will now apply our model to 4 different homes. Home 1 is a 1-story single-family residence built in 1953. Home 2 is a ground floor unit located in an 8-unit complex built in 1967. Home 3 is a 15th floor apartment located in a 30-unit complex built in 2003. And Home 4 is a 2-story single-family residence built in 1990. On the left, we show our input parameters based on the curated M3 dataset, and on the right is our results. We found that Home 3 had the greatest temperature fluctuation due to its small size and lack of shade, whereas Home 1's temperature remained relatively stable due to its deep shade. To validate our model, we searched for real-world examples. A WREG Memphis report from the June 2023 heat waves shared that a resident's home reached up to 89 degrees Fahrenheit. This converts to roughly 31.7 degrees Celsius and aligns with our model's prediction for Home 3, highlighting its real-world relevance. To analyze the sensitivity of our model, we jittered 2 parameters. On the left, varying the amount of sunlight that was hitting the home through the global horizontal irradiance found that it had a significant effect on indoor temperatures, whereas variations in the R parameter representing the wall insulation had minimal effect. The main strength of our model is its adaptability to multiple dwelling-specific characteristics that can be easily determined, though we understand that it is fairly rudimentary with its assumption that all expert guidelines are being followed. I will now pass it on to Raymond to explain our second model. Q2 asked us to predict the peak demand that Memphis should be prepared to handle during the summer months this year and 20 years from now. In the provided dataset, we were given the Shelby County's annual electricity consumption in kilowatt hours. However, if we simply conducted a univariate time series analysis, this graph will quickly extrapolate to 0. And also, is this even the metric that we want? Looking at this graph back from Q1, we see that indoor temperatures peak after outside temperatures, indicating that people will be using more power for cooling in the evenings. If this increased power usage is excessive, this could lead to a power outage. Hence, we use peak hourly load alongside total consumption to define peak demand. Whereas total consumption tells companies how much energy they should be generating to sustain a population for an entire month, peak hourly load tells them how much power the grid should be able to transmit for any given instant. We then chose 2 key predictors for peak demand, population and maximum temperature, and plot them side by side with our peak demand variables. We see that peak hourly load shows the same W shape as maximum temperature, and that total consumption shows the same downwards trend as population.
This motivated us to use our multiple linear regression as shown here for its interpretability and simplicity. Despite the p-values for the peak hourly load multiple linear regression being around 0.1, this multiple linear regression had the best R-squared and adjusted R-squared of the other models that we tested, including against only M-temp, only population, or both maximum temperature population, and also a peak or a lagged dependent variable by 1 year. To forecast 2025, we used the World Population Review 2025 projection for population and the maximum of the max temperature values for a more safe and conservative estimate for the short term to obtain a peak hourly load of 3,433.7 megawatts and 887 million kilowatt hours for total consumption. To forecast 2045, we used the SSP scenarios and their projected 2045 global changes in temperature, whereas the most optimistic SSP 1-1.9 explicitly stated the 2045 global change in temperature in accordance with the Paris Agreement. The rest did not, so we had to calculate them using the below transformation, which is in line with our first assumption that projected global temperature growth is approximately linear over the 78-year period from 2022 to 2100, as future changes in global temperature is based on highly unpredictable physical, political, and industrial factors. We also assume that there are no major technological advancements that improve AC technology in the next 20 years, as it is extremely difficult to predict the onset and impact of innovation. To forecast 2045, we use the University of Tennessee's Boyd Center's 2045 projection for population and the various scenario-adjusted global changes in temperature to get a maximum peak hourly load of 3,563 megawatts. For sensitivity analysis, we analyze the percent differences of the max and min values for peak hourly load and total consumption respectively, and we get these low percent differences in spite of fairly significant changes in temperature, indicating the resilience of our model. The biggest strength of our model is the use of regression analysis over univariate time series analysis with two key predictors that make logical sense in the context of the problem. Additionally, we use scenario analysis, which is in line with expert projections in the literature. However, since our model is based on expert projections, it may require dynamic revisiting as these projections change over time. Also, we could have investigated more additional variables, including other demographic factors or climate factors. I will now pass it over to Vivian to talk about Q3.
Question 3, Beat the Heat, asks us to develop a vulnerability score and use them in order to help Memphis neighborhoods equitably allocate resources for minimizing the effects of a heat wave, such as in Q1, or a power grid failure, such as in Q2. To guide our model, we established 3 key assumptions. First, that the effects of a heat wave fall under 3 key consequence types: population health, agricultural loss, and building or infrastructure damage. This allows for a comprehensive review of all heat wave impacts. Additionally, fatalities and other health complications can be monetarily quantified using value of a statistical life. Following federal standards, we treat 1 fatality or 10 severe injuries as $11.6 million in economic loss, allowing for a common unit of measurement across our key consequence types, leading us into our final assumption that heat wave effects can be monetarily quantified using expected annual loss, or EAL, which is the combined sum of our 3 loss types. This is a standard metric used by FEMA's National Risk Index to estimate the long-term effects of natural hazards, or in our case specifically, heat waves. We define our vulnerability score as a measure of a population's susceptibility to harmful effects quantified by EAL due to a heat wave. We collected census tract data from FEMA in order to sum those EAL values of census tract that overlapped with the zip code boundaries of Memphis neighborhoods. But we then wanted to analyze what predictors could accurately predict the severity of these losses, leading us to use a multiple linear regression to analyze the relationship between neighborhood risk factors and the predicted expected annual loss. Our initial regression involves several potential predictors identified from current literature shown below. But while socioeconomic factors such as age or income are correlated with heat wave vulnerability, they're also correlated with each other. And these intercorrelations could lead to a misleading or inaccurate regression. To address this, we implemented backward variable selection until all predictors were statistically significant. Our 4 final predictors were the proportion of households with elderly, the proportion of households with children, the total population, and the number of residents aged 16 and older who commute via walking or public transport. We then constructed our vulnerability scores using the previously identified predictors with the regression coefficients as their weights. These vulnerability scores were then normalized using min-max scaling and finally multiplied by 100 for an interpretable and standardized scale from 0 to 100. Now, Ramya will discuss our vulnerability score results.
The map depicts the geographic impacts of the vulnerability on heat waves, with darker red shades indicating higher vulnerability and darker green shades indicating lower vulnerability. This map allows us to identify high-risk areas of Memphis, such as the east and west corners, guiding resource allocation. Additionally, the table depicts the 10 neighborhoods with the highest vulnerability scores, which would benefit from targeted intervention. Our results identified the neighborhood with the highest vulnerability as Hickory Wide, with a score of 100. Hickory Wide stands out due to its large proportion of households with elderly individuals and children. On the other hand, downtown has a score of 0, which makes intuitive sense given its urban and younger demographic profile. This indicates that age demographics play a large role in vulnerability due to heat waves. To assess the reliability of our model, we conduct a sensitivity analysis. We jittered our parameters and found that the average percent difference in our vulnerability scores was only 3.47%, indicating that our model is robust against small changes in our input parameters. We offer the following policy approach to Memphis based on our model, which we discussed with our congressman who approved of its feasibility and legislative ability. We think that we should install cooling centers in high-risk areas, shade structures at transit stops, and offer tax incentives or rebates for shade solutions to both homeowners and landlords. Our biggest strength lies in our use of expected annual loss, which not only accounts for outcomes in health, but also agriculture and building value. However, we could consider additional predictors, and correlation does not imply causation. Overall, this challenge asks us to model how Memphis can prepare for the growing threat of extreme heat, from individual homes to the city's infrastructure to its most at-risk communities. For problem 1, we used a differential equation model, finding that shade coverage alone can lower indoor temperatures by several degrees. For problem 2, we used a multiple linear regression with scenario analysis, finding that Memphis will need to support a peak load of over 3,500 megawatts by 2045, indicating a need for proactive grid investment. For model 3, we found that age demographics play a large role in vulnerability after a heat wave. At the end of the day, these aren't just models. They're about real people affected by heat waves, people experiencing homelessness, people unable to afford AC, elderly, children, and the mother in Memphis struggling just to help her daughter breathe are at risk. Our goal is to equip Memphis with the tools to act early, efficiently, and equitably. The risks are rising, but so is our ability to protect the people most affected. Thank you.
Okay, thanks so much. Susie, do you want to start us with a question?
Thank you. Thank you very much for your presentation and all your work. Like 2 slides back, maybe. You have your vulnerability scores, and you talked about your recommendations.
Yes.
And did you say you had a discussion with the policy? Was that a real discussion, or was this a synthetic discussion?
No, so I had access to our congressman, which is known for his policy advocacy. And after we found out that we were being finalists, we realized that we should reach out to him and discuss if these policies were even legislatively feasible and fiscally feasible. And what he told us is that they not only align with our federal priorities, but they would also make Memphis eligible for federal resilience grants, ensuring that they don't bear the burden alone.
This is wonderful. So this is really the goal of M3, get you thinking and working on real world problems. And I'm glad you followed up. So thank you. This is awesome.
Okay, my question is about your part 1. Your model to predict the indoor temperature included several factors that affect the heat transfer. What other factors did you consider, or if you were to start the problem over, would you think about any other factors to consider to include into your model?
Yeah, absolutely. So scientifically, our model is based on a physical law that requires the assumption that the indoor temperature is uniform across the entirety of the home. Now, this is not necessarily always true. There are plenty of, for example, heat pumps is a new and upcoming system that is designed to redistribute heat throughout the home that may influence the presence, like the distribution of temperature and thus the efficacy of heat transfer across walls and solar radiation. Now, we chose not to consider some of these factors due to, number one, for example, heat pumps not being extremely prevalent in architecture yet, as well as simply keeping the model relatively simple. It is a lot of factors to consider, and as you can see in our final equation, it's already quite complicated. And ultimately, we decided that this was sufficient due to its alignment with the expected values, especially found in newspaper articles, as we demonstrated on one of our later slides. Yes, right there.
Thank you.
Thank you. I have a question about your vulnerability score, in particular about the coefficients. In your results, your coefficient for population is negative, and your coefficient for the median household income is positive. What was your reaction when you saw that, and what are the implications for what that means for your score?
Yeah, it actually did confuse us at first because we thought, oh, population-wise, the coefficient negative. But after analyzing Memphis as a city itself, we also saw that population recently has been declining, which could also contribute to the negative coefficient.
Remind me, these coefficients came from a least squares regression, and what was the variable being predicted?
The variable being predicted was expected annual loss.
Okay, which was obtained, like, this is published by someone, or where's that data from?
It was from FEMA's National Risk Index, the census tract data.
Ah, okay. So it's not clear to, maybe I'll push back on that answer a little bit. It's not clear to me why Memphis's declining population would factor into that.
So the negative coefficient basically means as population increases, so loss decreases in like these certain areas, right?
Okay.
So then this means that while population is increasing in a certain neighborhood, what it also means is that it's getting more urbanized and there's more factors and more cooling centers, more ability for Memphis currently to support people dealing with the effects of heat waves. So that's why we hypothesized that population had a negative coefficient, and median income. As median income increases, I think it's a similar thing where number one, it wasn't statistically significant. So we found that in the end, this actually didn't play into our model. But this is definitely something we would definitely look into further and maybe research about like the income demographics and how income is spread throughout Memphis by even analyzing a heat map of income versus the heat map that we created.
Okay. Okay, it makes sense. So it's like the declining population is telling us something different about the neighborhood.
Yeah.
Yeah. I have one final question. Which was so for part 2, I love to use these SSP scenarios because as we saw from Professor Mura's talk, that's sort of like an industry standard. One thing I wanted to ask about is they have these projected global temperature changes, which I guess is a projection of average global change. And I'm wondering, do you believe that will change? Like how will the change in average temperature impact the change in, say, peak temperature? Like at the end of the day, for this question, you guys emphasize peak power use. So what's the connection between this like average temperature change and say peak temperature change in the city?
Yeah, so we noticed that, and actually in our 2045 projections, we added these average changes in global temperature to the average peak temperatures from the average maximum temperatures from the provided data set from 2012 to 2022. So instead of using 103 degrees Fahrenheit for a short-term estimate, we used 99.14 degrees Fahrenheit, which is the average of all the 10 data points that were given. And you asked about the,
like, I might think, I'm just guessing. I might think that the increase in peak temperature would be more than the increase in the average.
Yeah. So I get to forecast 2045, since this is long-term forecasting, we thought it would be, we use the averages for a more like robust estimate.
Okay.
Yeah, but we will definitely look into that further.
Okay, cool.
I think I understand what you're saying is that that these peak temperatures would probably increase more due to these climate changing concepts, though these again depend on very variable factors like political, economic, and other social things that we can't easily predict. So we decided to just use the average temperature in these changes to predict our model right now.
Yeah, that makes sense. Okay, let's thank the team. So your representative, yeah, go ahead. If you want to say words of thank you, this is the time to do it.
Yeah, sure. I want to thank, first of all the organizers for M3 Challenge and Cyan for hosting us. Also Jane Street for giving us this wonderful venue and making this day possible. I want to thank our parents back at home, our teachers for being like such a valuable audience and giving us great advice when preparing for a presentation. I want to thank first and foremost, our coach, Mrs. Everett, and her husband for helping chaperone us here in New York City. It was a really fun time here. Yeah, thank you. I'll just click to the end.
A couple minutes early, but let's just wait because if people tune in on the live stream. All right, you guys are gonna have 15 minutes to present. I'll give a 5-minute warning, a 2-minute warning, and a 1-minute warning. It's not super easy to see me over here, so just make sure you glance occasionally. And then we'll do 5 minutes of questions, and you'll have time to thank people at the end. Let's give it 1 minute. Oh, by that clock, my phone's a little slow. Okay, we'll get started. So when you're ready, please introduce yourselves, and then you can begin, and I'll start your timer.
Good morning, judges and audience. My name is Tianle Liang.
My name is Prabjay Chandran.
My name is Truman Graves.
Are we ready? Yeah, good to go. All right, thank you. Good morning, judges and audience. Today, we are excited to present our take on the hot button issue, staying cool as the world heats up. I'm Tianle.
I'm Prabjay Chandran.
I'm Truman, and we're from Zionsville High School. Our research focused on how Memphis, Tennessee can best prepare for extreme heat events. In question 1, we used Newton's law of cooling to model the temperature in non-air conditioned homes over a 24-hour heat wave period. We saw that apartments were 1.45 times as affected as single-family homes. In question 2, we projected peak grid demand over the summer months for the next 20 years. Our model saw a 20% increase by 2044, meaning that Memphis will need to upgrade its power grid to better prepare. In question 3, we created vulnerability scores for all 27 Memphis neighborhoods, which can be used to adequately address policy issues. We hope that our models will prove indispensable to Memphis policymakers as they seek to protect their communities for years to come.
We'll begin with the first 3 challenges facing the city of Memphis: speedy transfer of heat into non-air conditioned homes. To analyze this, we've developed a model predicting the changes in indoor temperature of a non-air conditioned dwelling over a 24-hour heat wave period. We chose Newton's law of cooling as the core of our model for 2 important reasons. First, it directly reflects the physical reality of heat flow, tracking how indoor temperatures of a non-air conditioned home change based on outdoor ambient temperature changes. The second most important reason is that it's a simple yet very powerful model. It directly reflects things like HVAC, building engineering, and also ASHRAE standards, so we can adapt our parameters based on that. Like I said, we didn't just stop at the basic Newtonian model. We adapted it based on parameters from ASHRAE standards. We added a solar heat gain quotient, A. This reflects things like windows causing heat to be transferred inside the building. We also added a constant internal heat gain quotient, Q. This represents things like people and appliances within the home that generate heat. Overall, these 2 made our model more realistic without making it too complex to solve. By taking it from the ASHRAE standards, we can map this out for both apartments and single-family homes, the 2 most common home types in the Memphis area. Our values K, A, and Q are as shown for both single-family homes and apartments. As you can see, the respective values for K, A, and Q for apartments are higher than the respective values for single-family homes. This is due to show that apartments transfer heat inside significantly faster than do single-family homes. This is due to 3 key reasons. First, apartments have worse insulation. They have more cost-effective materials and thinner walls, meaning heat transfers inside significantly faster. Second is solar heat. Apartments have more windows, especially in multi-story buildings when this becomes a bigger issue as solar heat transfers inside significantly faster. Third is occupancy density. Apartments often house more people in a smaller amount of space, leading to a higher Q value as shown.
Here you can see our model graph for the given data from M3. As we can see, apartments are much more volatile to heat transfer than single-family homes, which we also see reflected in the respective maximums. Specifically, apartments are 1.45 times as affected by ambient or outside temperature, 1.6 times as affected by solar heat gain from the sun, and 1.25 times as affected by internal heat generation, showing they are overall much more volatile to heat transfer. Now onto our sensitivity analysis. We shocked both of our ambient temperatures by 2 degrees Celsius, and you can see the corresponding shifts on the graphs here. Our apartment model shifted by 1.98 degrees Celsius, and our single family model shifted by 1.9 degrees Celsius. We can see that this means that apartments are more vulnerable to changes in temperature due to lowered insulation standards compared to single family homes.
Let's move on to question 2. During summer months, AC and household appliance usage spikes, putting a strain on the Memphis grid called peak demand. In question 2, power hungry, we are tasked with modeling this peak demand for the next 20 years. Before even modeling, we first had to create a reliable data pipeline to extract Memphis demand. We used open data from the US Energy Information Administration for the whole US region, extracting monthly peak demand and then factoring in annual customer counts to create this metric, monthly demand per customer. And then from M3's provided data, we calculated a 1.4 times ratio between Memphis and US demand, and thus calculated the peak summer monthly demand per customer in Memphis from 2001 to 2024. We also had to prepare our explanatory variable, heat wave temperatures. We saw a very special pattern in this, namely the sinusoidal and the cyclical pattern in temperatures. So we decided to extend our explanatory variable with SURIMA, a time series that specifically targets seasonality. We optimized hyperparameters through AIC scores, testing 1,080 combinations of hyperparameters, reaching the seasonality constant S of equal to 5 years. In our results, we see these clear 5-year cycles, which actually makes sense because of climate patterns called El Nino and La Nina, which are weather phenomena that occur because of ocean winds. We projected a 70% confidence interval, which you can see shown in red here, and the graph shows both historical data and projected data. We see in the next 20 years, the average heat wave peak temperature will reach 38.96 degrees Celsius, up 1.5 degrees from the last 20 years. Now that we have both the explanatory, heat wave temperatures, and the response, peak demand per customer, we were able to move on to our main model, gradient boosting with XGBoost. We chose gradient boosting because of its historical relevance in climate modeling and the robustness to overfitting. We optimized hyperparameters using mean absolute error, MAE, reaching around 80 kilowatt hours. In the next 20 years, we see a 1.45% increase in peak demand per customer with a 1.77% increase per 1 degree Celsius increase. In this final slide, we show the peak demand we projected for the entire Memphis grid. We started off with projecting peak demand per customer, and now we multiply the actual customers in the Memphis grid around 431,000 in 2024 and factored in a 0.6% population growth rate. In 2044, we see around a 1.76 billion kilowatt hour projection for the peak demand, which is up 20.2% from 2024, putting a drastic strain on the electric grid if there are no large infrastructure renovations. Now on to question 3.
Our final question combines math modeling and urban policy. We're tasked with developing vulnerability scores from heat waves for 27 neighborhoods across the Memphis area to help policymakers allocate resources more equitably.
We started off with 22 neighborhood variables, which is too much to analyze. So we don't have a label, right? So we had to make our own vulnerability metric. We first started off with an unsupervised learning technique called principal component analysis, PCA, projecting the original 22 variables into an orthogonal feature space, creating 4 principal components called PCs. This was very effective, not only simplifying the problem, but also preserving nearly 85% of the original variance. If you can see on the board here, PC1 represents the highest explained variance ratio called EVR, PC2 represents the second highest, etc., etc. On this slide, we can see the PC results with their respective EVRs. We can see that PCA was not only very effective, but also very interpretable. If you look at PC1, you see that the top variables by loading factor are households with 1+ vehicles, population age 16 plus working, and the primary work transportation is driving. We see that these 3 variables all represent their sector workforce mobility very well. Similarly, PC2 represents aging urban density, PC3 represents housing diversity, and PC4 represents development and income. Our PC results that we got were not just random, but actually represent real-world socioeconomic sectors. We summed each of the PCs, weighted by the respective EVRs to get our final goal, the vulnerability index. And we chose positive or negative contributions based on their specific relationships with vulnerability. For example, PC1, workforce mobility, is negated because workforce mobility, when it goes up, vulnerability naturally goes down. This is similarly shown in PC4, development and income. However, in PC2 and PC3, aging urban density and housing diversity, they remain positive because they have direct relationships with vulnerability. Our equation is shown below.
Here you can see our vulnerability scores graphed on a map of Memphis, Tennessee, with higher vulnerability scores in a deeper red and lower vulnerability scores in a deeper green. As we can see, PCA is very easily interpretable. The most vulnerable neighborhoods are concentrated on the western side of Memphis, where there's higher urban density and poorer communities. That's also where downtown is. On the other hand, the least vulnerable neighborhoods, such as Collierville, are concentrated in the wealthy outer suburbs. You can see here our top 3 least and most vulnerable neighborhoods. We hope that policymakers will pay key attention to geospatial risk distribution in order to ensure an equitable use of resources.
For our sensitivity analysis, we analyzed how changing the weights of our principal components impacts our vulnerability scores. We began by shocking the EVRs, essentially the weights of each of our principal components in isolation, discrete percentages of 10, 20, and 30%. PC1 and PC2, workforce mobility and aging urban density respectively, showed the most variation, a total of 70% of the total variation in our model. However, this is more than manageable as this is expected considering its high impact. PC3 and PC4 showed significantly less variation and their influence is more stable. Overall, our PCs remain robust, even in the face of short-term dominance from particular socioeconomic areas. We then made a new addition to our initial sensitivity analysis that included Gaussian perturbation. Essentially, we added a random Gaussian noise to 22 input variables by 10% of their original standard deviation. This was done in order to then find the loading factors and see the structural interpretability of the PCs remained robust. As shown, they fairly did. PC1 and PC2 showed little variation and not much vulnerability to our Gaussian perturbation, meaning it's significantly robust. PC3 and PC4 did show significantly more variation. However, this is more than manageable as their influence on the ultimate vulnerability scores are fairly minimal compared to PC1 and PC2. Overall, each of our PCs remain robust, showing that policymakers can practically implement this and our results can be replicated in future studies.
So what can policymakers do with these vulnerability scores? Well, we propose a 3-pronged strategy. In areas with vulnerability scores of 70 to 100, we can look towards direct intervention strategies. One example would be grid hardening, which prepares the power grid for inclement weather events and has been shown by FERC to boost GDP by 2.5 million for every 1 million spent. We would also look towards cooling infrastructure in these most vulnerable areas. In areas with vulnerability scores of 30 to 70, we would instead look towards time of use pricing, which varies rates throughout the day based on demand and has been shown in California to lower electric load by 11.1%. In the least vulnerable areas with scores in the range of 0 to 30, we would rather look to passive strategies, such as public awareness campaigns around responsible use of power to mitigate the effects of climate change. With this multifaceted approach, Memphis policymakers can ensure an equitable and just action plan for their communities.
To conclude, we began by developing our adaptive Newtonian model to model the increase of heat temperature inside homes compared to the outdoor ambient temperature during a heat wave period. We found that apartments are significantly more susceptible to heat waves, with temperatures reaching 42.1 degrees Celsius. This should prompt policymakers to make sure insulation is not only cost effective, but it also can withstand even the worst of temperatures to make sure families have healthy living conditions. Second, we use Sarima XG Boost to model the peak demand of electric grids over the next 20 years. We found an average temperature over the next 20 years in Memphis of 38.9 degrees Celsius. This is a whopping 1.5 degree increase over the past 20 years. This should prompt policymakers to scale infrastructure alongside working with electricity companies to make sure demand can be met. Finally, we used a PCA model to map the places of highest risk in the Memphis area. We found the most susceptible and at-risk areas to be in West Memphis in comparison to a least at-risk place in East Memphis. This should show that policymakers should implement a tiered response in terms of allocating resources equitably.
There's a lot of future work that could be done, both in terms of research and policy. In question one, we could look towards creating a vertical temperature gradient to show the effect of heat waves on multi-story buildings and towards improving insulation and roofing standards in Memphis and in the surrounding areas. In question two, we look towards creating a Monte Carlo simulation to stress test our model and creating an electricity price fluctuation model that will show the effect on ratepayers of our current model. In question three, we would look to directly integrate meteorological variables, which are currently only implicitly integrated through other variables. And we would cross-benchmark our model with ensemble learning methods to ensure its efficacy. Thank you for your time, and we're now ready for questions.
I can start with one. So I thought the principal component analysis was interesting. You ended up with very interpretable principal components, which isn't always the case. It'd be like a cool example from my machine learning course. But I want to better understand what the value of the principal component analysis was. At the end of the day, as I understand it, you hand assigned like a ±1 score to each of the depending on your that got multiplied by your weight in each individual principal component. You could have in principle done that for the original features without doing a PCA. So can you explain to me like what is PCA adding to the model?
Yeah, so PCA's point is to have a dimensionality reduction. So we started off with 22 socioeconomic indicators. And if you actually look at the variable names, you have a lot of similar variables. For example, we had 5 variables that were like houses aged 1970s to 1980s, houses aged 1980s to 1980s to 1990. There's a lot of multicollinearity in there. So we used PCA because of its efficacy in reducing that multicollinearity and also making it much more interpretable. If you can see our main PCs, we have 4 very clear, broader socioeconomic sectors here. And those 5 variables that I just mentioned, the age of the houses, all 5 of those variables represent the same thing. And they're all grouped in around PC2.
Yeah, that makes sense. Thank you.
I have a question and the way you address problem 2 in terms of using the Sarima model. There's certain parameters associated with that. There's assumptions about the data. Could you comment about the parameters you chose and how you chose them, and about the data and how you tested the data?
Yeah, could you repeat that question?
So using Sarima in question 2, how did you choose these parameters, and how did you look at the assumptions associated with the method in terms of the data?
Right, so I'll start with the assumptions. We are modeling, first, this is the explanatory variable. We are modeling heat wave temperatures. So as you can see on the screen here, there's clear 5-year patterns, even in the historical data. And we are able to find this pretty reasonable as an assumption because of real life weather patterns called El Nino and La Nina, which are cyclical. So noticing this sinusoidal pattern, we chose to use Sarima instead of just a regular ARIMA. In terms of the parameters that you asked about, we optimized those from 1,080 combinations of hyperparameters, and we used this AIC score information criterion to reach these optimization results that you see on the board here.
we did make significant assumptions in relegating the temperature to the peak grid demand because we didn't account for things like people moving in and out of the city or industry, some economic details that would boost electric grid demand without being directly related to the temperature. We did assume that temperature relates to higher AC usage, the main demand on.
Okay. And when you say you optimize them, what does that mean?
So basically, when we tested all of these combinations and we tested each of the AIC scores and we picked the lowest one, whichever hyperparameters that corresponded with the lowest
one. Measure of?
It is the measure of how essentially, I believe, how similar or how each of these PD and Q and capital PD and Q, how well they are match of the data.
Okay.
And lower the score, the better.
Okay.
Do you use any software to do this analysis to determine PD and Q?
Can you repeat that?
Did you use any software to find those P, D, and Q?
Yeah, so we used simple Python. This is really just a for loop. Because PD and Q, so PDQ, PDQ, that's six different parameters plus the S, so that's 7. And we have a couple of combinations of each within their respective realistic ranges, and that's just a for loop.
Did you look at the assumptions, how valid your SARIMA model is? Did you check the assumptions?
So which assumptions would you like to?
What the data, residual analysis, autocorrelation function, anything like that? That's okay if you didn't.
We estimated a 70% confidence interval for our SARIMA results for the peak grid demand because there are some variables I discussed earlier, like people moving in and out of the city, things outside of temperature essentially that we didn't account for because that would make the model incredibly complex and wouldn't be realistic for time frame we were given. These are some additions we can make to our model to increase that 70% confidence interval to something significant.
Okay. Mainly, our model was focused on the fact that there's these 5-year cycles that with SARIMA rather than.
Sure. Yeah. Thank you.
Any other questions? Okay, with that, let's thank the team. So Zionsville, if you guys want to say a few words of thanks, now's the time.
Yeah. Today, we would like to thank SIAM and the organizers of M3 for providing us this opportunity to compete and to present our solutions. We would also like to thank Jane Street for hosting us and our judges for reviewing our solutions vigorously. We would also like to express our gratitude to all the people that have supported us throughout our journey, including our coach, Dwight Moser, and our families and our school principal, Karen McDaniel. Over the course of this challenge, I think we really grew as problem solvers and critical thinkers. We were able to create working solutions, even with a small team of 3 under just 14 hours, which I believe was a very big learning experience for us. In our hometown of Indiana, this topic of heat waves and outages isn't really relevant to our daily life. So we'd like to appreciate M3 for bringing in this new and diverse experience for us. We're excited to meet with everybody here and learn from your solutions as well. Thank you.
You can try and stand over. Don't stand this.
Okay. Welcome Ride Country Day School. We're going to get started in a minute. So you're going to have 15 minutes to present. I'll give you a 5-minute warning before the end, 2 minutes, and then 1 minute. Just glance over to me occasionally because you'll be mostly focused that way. And then after 15 minutes, we'll do 5 minutes of questions and you'll have a moment to thank whoever you want to thank. Okay. Let's give it like till 10 because if there are people coming in on the live stream, and then I'll say and you guys can get started. When you get started, start by introducing yourselves so we hear everyone's names.
Use the podium microphone.
Yeah, either or. Those ones work as well. Yeah.
I'll actually go.
Okay, whenever you're ready, introduce yourselves first and then you can get started.
Sounds good. Hello, everybody. My name is Jay Minding, and I'm currently a senior.
My name is Dana Ballin, and I'm currently a senior.
My name is Alyssa Chu. I'm currently a senior, but I'm sick today, so I won't really be talking.
And my name is Jonathan, and I am a junior.
Good morning, judges, guests, and other competitors. We're Team 1A015 from Rye Country Day School, and we're here today to present on this year's M3 challenge problem, hot button issue, staying cool as the world heats up. Our goal with this year's problem was to investigate the effects of heat waves on the communities that have the highest stakes in these crises. Specifically, we wanted to explore the effects of heat waves on the community of Memphis, Tennessee. With that in mind, we were asked to address 3 questions, the first of which is hot to go, where we developed a model to predict the indoor temperature of any non-air conditioned dwelling over the course of a 24-hour period during a heat wave. We began with 8 initial assumptions, the first 3 of which relate to the initial temperature of the indoors. We began by saying that the initial building temperature starts as the same as the outdoor temperature and that it does not vary significantly from the outdoor temperature. In addition, we assume that the outdoor temperature stays constant at every point around the building. The next 5 relate to the building's geometry, and we said that the rooms are square in floor plan and equal in size, that the ceiling height is 2.4 meters, that houses modeled are made of wood, that heat enters the houses through the walls and ceilings only, and that the thickness of each of the walls and ceilings is a foot each. We originally given data for the outdoor temperature by the challenge itself, which you can see plotted over here in blue. Going by the shape of the blue dotted points over here, we determined that a sinusoidal fit would be the best way to come up with a model for the outdoor temperature. And so we regressed an equation for the sinusoidal equation, which is shown on the left over there. We found that it had an R-squared value of 0.97, indicating a relatively accurate fit. We then began with Newton's law of cooling as our base model for the indoor temperature, where the rate of temperature change is dependent on a cooling coefficient and the difference between the indoor temperature and the outdoor temperature. We decided that this model would be a good choice because it is computationally efficient and represents the primary mode of heat exchange in this scenario. In addition, it works well when the differences between the indoor and outdoor temperatures are moderate. Since we were able to regress an equation for the outdoor sinusoidal temperature, we substituted that in for T sub S as shown in the original differential equation over here. We then recognized that this was a linear ordinary differential equation and expanded it, which is shown on the bottom over here. We used this analytical solution and applied it twice to represent the heat transfer from the exterior to the wall and from the wall to the interior. The results of which are shown over here. As you can see, there is a thermal lag, which is to be expected between the outdoor temperature and the indoor temperature. And the thermal lag ranges between 45 minutes to an hour, approximately. The maximum predicted temperature for each of the homes is around 38.4 degrees Celsius. We then performed a sensitivity analysis on our results to ensure that the model was stable. So we averaged the coefficient of variation over 10,000 trials with an average 5% variation in each of the inputs to mimic real-world uncertainty, and found that there was an overall 5.5% uncertainty within each of the models. This indicated to us that overall, our models were resilient to random error. So our primary strengths were that we were able to use an actual physical model, a widely accepted physical model, to come up with our base model, and we had an analytical solution with parameterized features that allowed us to gain insights into the long-term behavior of our solution. In addition, we had a realistic thermal lag, which was shown in our graphs. However, we did assume a simplified geometry for the buildings, and we weren't able to account for internal heat feedback from the inside sources.
So with the newfound knowledge that temperatures inside a dwelling without air conditioning can reach almost as high peak temperatures as outdoors in a heat wave crisis, we sought to look through the lens of the power companies, who are tasked with supplying the increased energy for people who want to stay cool as the world heats up. So we moved on to the second question, power hungry. We were asked to develop a model to find the peak demand in Memphis's power grid during summer months, both now and 20 years from now. We assumed that there would be no drastic changes to the rate of climate change and that there would be no drastic changes to the population trend of Memphis, Tennessee from the previous 10 years. We also assumed that the monthly electricity consumption of East, South, Central USA would mimic that of Memphis and that there would be no power disconnects during any given heat crisis. So we started our analysis by finding which factors could best indicate future consumption. We did this by using the Pearson correlation coefficient with results seen on the heat map to the side. As you can see here, the temperature of the month with maximum electricity usage was the best indicator of consumption with an R value of 0.77, which is above the generally accepted value of 0.7 for a strong correlation. We then sought to verify this correlation further by normalizing both the average values of temperature in July and August, which tend to be the hottest month, and the average monthly consumption. This time we got an R value of 0.83, which is once again above 0.7, a p-value of 0.0005, which is far below the generally accepted p-value of 0.05, and then a root mean squared error of 0.015. So this justified our correlation. So then with that in mind, we had the task of predicting the temperature, which we could then use to find the electricity consumption. We chose to use a linear regression model, as shown here, and found that the average temperature would increase around 0.02 degrees Celsius each year. We then looked to further justify that, though, by looking at world temperature data, which also showed a 0.02 degrees Celsius increase each year, and then also the climate.gov estimate of, once again, 0.02 degrees Celsius each year. So now we had to reverse engineer that temperature data to the consumption data. We started with an inverse normalization to find the peak consumption demand, and then we did a proportionality estimate between the Eastern, South, Central United States and Memphis. This was done using past values for the consumption of Memphis divided by the consumption of the Eastern, South, Central United States. And then we further verified that by using the population of Memphis and the population of the Eastern, South, Central United States. And as you can see here, these both got relatively the same value of 0.033. So with this process in mind, we found the average temperature both now and 20 years from now. In 2025, we found a 33.1 degrees Celsius average temperature. And in 2045, we found a 33.6 degrees Celsius average temperature. And these correlated to a 1.04 times 10 to the 9th kilowatt hours and 1.0818 times 10 to the 9th kilowatt hours, respectively, for Memphis electricity demands. So we were able to eliminate unrelated data through statistical analysis, and then we cross-verified results both for future temperature forecasts and for the proportionalities from Memphis to the larger area of the United States, and found that they were all relatively verified. However, we did assume a lack of policy changes, and we had a limited range of data throughout the years for all data points. We would also like to investigate temperature fluctuations each year in the future.
Despite the robustness of these power grids, there are still chances that power grids will fail in the case of a heat crisis. This brings us to problem 3, beat the heat, where we were tasked with developing a vulnerability score for various neighborhoods in Memphis to help equitably allocate resources to different communities in the case of a heat crisis or power grid failure. Our key assumptions were based off of which factors had an influence on the heat vulnerability. We said that a building's shape and size, building material, separation between buildings, which accounts for the urban heat island effect, and the amount of forestry and parks, open space in an area, all had an effect on heat vulnerability. There was also a CDC study done that looked into how socioeconomic conditions have an effect on heat vulnerability due to low communities with lower socioeconomic status not having as much access to key resources such as healthcare or cooling during these heat crises. The study also mentioned how elderly people and minors are more vulnerable than working age adults, and that people who take public transportation or who walk to work are more vulnerable than those who commute by car. So based on these assumptions, we were able to ask ourselves 6 key questions, which we use to determine the features that we want to include in our model. So based on these questions, we found that we want to include open space, housing, income, age, and transportation. And to weight all these features, we use a data-driven method known as an entropy-weighted model. So entropy is essentially a measure of the information gained from a feature, where if you have a high variability feature, like you see in green, you get a low information gain, and thus you have a high entropy. Whereas if you have a low variability feature, you have a high information gain and a low entropy. Because of the higher information gain, low entropy features are generally weighted higher than high entropy features in an entropy-weighted model. To construct this model, we first calculated a score for each feature, and then we normalized these scores for each neighborhood. We then calculated the entropy for each feature over all of the neighborhoods, and then used those entropy values to calculate the weights for each feature. And to outline some of the scoring methods, we did this as follows. So age was taken as the proportion of elderly and young people to the total population. Income was the average income in a neighborhood. Housing was a weighted average of houses built by decade. So if you had a house built 5 decades ago, it would be marked with a coefficient of 5, 4 decades ago with a coefficient of 4, etc. Open space is a measure of the total open space in the neighborhood, and transportation is a weighted average of commuter types. So if you have someone who commutes to work by car, they'll be weighted once, whereas someone who commutes to work by public transportation or who walks to work would be counted twice. So running these weights on our data set, we found the following. We found that income and open spacing had the highest impact on a community's vulnerability score. And using these weights, we were able to get scores for each of our communities and multiply that by the community's population to find our final scores. As you can see, Uptown and Prince District had the highest score, while East Memphis and Colonial Yorkshire had the lowest. Based on these scores, we were able to allocate resources as follows. So half of the resources of Memphis were allocated equally to each community, while the other half were allocated proportionally to each neighborhood based on their score. So Uptown would have the most, and East Memphis would have the least. We were able to create a very strong predictive model using the data that we were given, and we used data-driven methods to derive our weights. In addition to this, we were able to quantify our resource allocation guide for Memphis, where the resources can be interpreted as water distribution or creating cooling centers in different areas with respect to the percentage that we're allocating resources. However, some of our feature hyperparameters could be refined, and there were some features that we wanted to include in our model, such as building shape and size and building material, that were not given, and so we could not really implement those.
So throughout this problem, we sought to look at heat crises first by identifying and understanding the problem itself, then looking into primary interventions, and then finally secondary countermeasures in case those primary interventions fail. So we looked at the first question, which asked us to compare outdoor and internal temperatures. We did this by solving a linear ODE for an analytical solution and then validating our model using the Monte Carlo method. We found that there is a temperature lag from indoor and outdoor temperatures. However, they can reach almost the same extremely dangerous high of temperatures. So with this in mind, we look through the lens of power companies who are tasked with supplying the demand of increased electricity during these times of crisis for people who want to stay cool as the world heats up. So we did this by identifying strong correlations using Pearson correlation coefficients. Then we applied a linear regression twice to model future conditions. And then we forecasted the demand of 2045 via scaling. However, as robust as these power grids are meant to be built, sometimes they fail. So we had to then look through government officials who are responsible for taking care of the people when these power grids fail. So we did this by identifying which communities needed resources the most. We identified 5 vulnerability factors and then used an entropy-weighted method to assign weights to these factors. Then we understood these factors and allocated resources proportionally to all of the neighborhoods in need. We hope that the solutions we found to these problems will not only aid city officials and power grid companies in Memphis, but all over the world to help them address heat crises accurately and save the people. Here are references, and thank you so much for listening.
Thank you.
Thank you very much. So what are the questions or the directions you would have liked to have pursued if you had more time to work on this?
Well, first, for our first question, as you can see, we looked at purely conduction as the form of heating through outside and inside. And realistically, there would be people walking around inside. There would also be windows, which would allow for sunlight to come in and kind of like a greenhouse effect, like cars work, where the heat would get trapped inside. So that would also impact the heating, which could actually increase the temperatures even further, which would make it even more dangerous for people inside. And then we also would have liked to look further into the lag between the external and internal temperatures a little bit more, because realistically, the entire wall wouldn't heat up all at once. It would heat up kind of gradually.
Yeah, and then I can talk about my part of the problem. So the third question, sorry, let's just fast forward to that. Yes, so again, for like the data-driven methods that we use, some of our feature hyperparameters could be tweaked. So that would be like refining, for example, the housing feature, right? We said that the vulnerability of a house was linearly correlated with how old the house was, but perhaps we could like investigate that further to ascertain if that was actually the relation. And then there are some features that we were not able to include in our model that we would like to include if we had more time and more data. And in addition to this, one other interesting application that we could have used for this would be an agent-based model where you can actually simulate the interactions between different members of the community and see how that vulnerability really plays out in like an actual simulated environment.
And I think for the second question, our predictions relied a lot on predicting the temperatures, sorry. And so obviously in real life, temperatures vary and they fluctuate. And we modeled them linearly based on literature that we read, because this is a relatively short-term effect. But we would also like to look into various other models for climate change, and also to look at whether these fluctuations have any periodic or seasonal patterns.
Can I ask a follow-up question on the model 3? So I want to understand these entropy weighted values more. I don't see how they're related to vulnerability. Like you mentioned it's a predictive model, but are we predicting anything about vulnerability, or is it just a measure of how variable the data is?
Yes. So you're talking about this? Yeah. So essentially, the entropy weighted model is basically if you have just this data in a vacuum, and if you don't really have the expertise to ascertain like if a given feature would be more important than another given feature. This is a great data-driven method to actually assign weights to these, because obviously we're not all like experienced in this field. And so we feel like our subjective weighting would be like deleterious to actually creating a good predictor for vulnerability. And so we decide to let the data speak for itself.
But why is a highly variable feature mean that it contributes more to vulnerability?
Yes. Okay. So I think there are two things that we need to talk about. So variability, as in like the statistic sense, like standard deviation, and then variation between y values as you for each x value. So if you can see for the high entropy feature, you have for all of the x values, there's little to no variation in the y values. So that means that the standard deviation of the distribution would be infinite, right? And that means that.
But what are the y and x values here? So the x is some number, like some measure about the neighborhood.
Yes.
And then what is the y here?
Yeah, so the x is just the samples, and then the y is the actual feature value. So in the case of income, it would be each of the neighborhoods, and then the income from that neighborhood would be the y.
So okay.
So if you remember also, like Jarnath said before, we don't really have a lot of expertise in the different ways that a community might be affected by each of these values. So in our assumptions, we basically assumed that they would all weigh the same after reading literature. In reality, I'm sure that certain things like socioeconomic conditions would have a higher value and weighting, but that is also biased from my own experiences. And we would like to take our own biases out of the equation. So we read a lot of literature, just finding which would impact communities. And then we decided to look at variation rather than our own biases to add it to a model.
Okay. I'm not totally convinced, but we can leave it. I think it's for future work. Yeah.
No, I think I can.
I want to give someone else a chance to ask a question, but I mean, I understand your answers, and I totally agree that it makes sense to try to come up with something subjective, which I mean, objective, which certainly you did, which is good. Yeah.
Yes, I do have a question. So in your question 1, your answers, your models are very similar for all 4 types of apartments or dwellings. Do you think this is realistic? Or I know you already mentioned that you could consider other factors, but what are those factors and how possibly they will change your model or models, because you have 4 of them?
I'll take this question. So as you mentioned, yes, the heating graphs for these do look quite similar. I think part of that is due to the fact that it's over a 24-hour period, and our thermal delay mainly comes in the form of like a thermal delay between the inside and outside, which happens over the course of approximately an hour, which is why it looks similar. Can you go to the next slide, please? If you go to the next slide here, you'll find that the more volume a building has, the longer it takes for it to follow the outside temperature, which is what we expected for. Can you go back a slide, please? Which is what we expected to happen physically. The other thing is that, like we mentioned earlier, we weren't able to take into account things like the amount of sunlight coming in through windows, or what orientation it's facing, or how much tree cover there is, because we thought that was more because for some of those are more categorical variables, while for others we figured that not enough data was provided so that we could truly incorporate those into an accurate model. And so in the future, if we were to incorporate those, I believe that it would show more variance in each of the graphs shown here. But for now, this is based on. Can you go back a slide? We based our model mainly on the outdoor temperature and conduction from the heat from the outside to the inside.
Right. So did I understand it right? The difference between those 4 apartments or housings is the lag when the temperature heat, but not the maximum temperature. Is that right?
Sorry, yeah. The maximum temperature is different for each of the houses, and I think if we had more time, what we could have done was perhaps find a better incorporation depending on the volumes of each of the houses. For now, the main thing that changed with each of the buildings here was the cooling coefficient, and that is what you see here. I think if we had more time, what we would have liked to do is do a little more research into the kinds of materials used in each of these buildings, because I think bigger buildings will use different kinds of materials, and so the peaks would be a little different.
Okay, yeah, thank you.
You have a question. You at the very end, you discussed your Monte Carlo simulations, and you talk about varying your data points. I was wondering if you could expand on that, give us some more details about what that means and how you did the calculations and what insights that gave you.
I'm sorry. Could you repeat the question? I couldn't hear it that well.
Sorry, you for your Monte Carlo simulation for the first question. You said you used 10,000 data points or 10,000 trials. You varied the data points. And I was wondering if you could give more details about what data points you varied and what insights you got from that.
Yes. Okay. So could you go back a slide, Zach? Yeah. So the main things that were taken into account here were the outdoor temperature, as well as the cooling coefficient, as well as, can you go back a few slides to the one where we did the regression, the one before this, before this. No, before this. Yes, there. As well as the parameters for the outdoor temperature. So we added random variance into those to model like real world uncertainty and random error that could occur, just from the real world being not as certain as it would be in a model. And so what we're trying to show is that even if we add in random error over the course of many different trials, that our model will stay resilient and not show an extreme amount of change from a small amount of change in the input.
Could you give some more details about how you added that jitter?
Sure, yeah. So we have an original value set here for we have original values set for each of the parameters we inputted here. And to those, like I mentioned earlier, we added a 5% like variance to each of those. So depending on what the parameter was, we took 5% of that and either added or subtracted somewhere in the range of like plus or minus 5% of that, and use that as the new input for each of the trials.
Okay, awesome. Thanks, guys. Let's all thank the team. And then if your representative wants to say a few thank yous, now's the time to do it.
I'd like to begin by saying a big thank you to our coach, chaperone, and math teacher, Mr. Mineo. He's our wonderful math teacher at school, and we really like to thank him for putting up with all our shenanigans in class. And on behalf of all the seniors on our team, we will miss you dearly as having you as our math teacher. Next, I'd like to take some time to thank the people who really brought us here. So our parents and our families who provided us support through every step of our journey on the way here. We'd like to give you all a big, big thank you for helping us get where we are today. Last but not least, I'd like to thank the hosts and sponsors for today's event, namely MathWorks, SIAM, and Jane Street. On behalf of the team, we really enjoyed being able to do math modeling and being able to participate in a wonderful event like this. And so we'd like to extend a huge thank you for making this possible. Thank you.
Good.
Yeah, welcome Haberdashers Boys School. So we'll get started in a minute. You're gonna have 15 minutes to present. I'll give you a 5-minute warning, 2 minutes, and 1 minute. Just peek over at me occasionally because I know you'll be focused your attention out there. And then afterwards, we'll have 5 minutes of questions. You can get started whenever you're ready. Just if we ask that you begin by everyone introducing themselves, and then I'll start your 15-minute timer.
I'm Oliver.
Wei Tao, famously known as 2Pi.
And I'm Arian, and we're team 17705 from Haberdashers Boys School from the UK, and here's our solution to the hot button issue. I'll now hand over to Oliver.
So in question 1, we were modeling the temperature inside a building during a heat wave. We chose the city of Birmingham in the UK, not in Alabama. We start with some simplifying assumptions. So most importantly, we assume the temperature in a building everywhere is constant. Otherwise, the model becomes pretty complicated. We also ignore humidity and wind speed since these affect perceived temperature more than actual temperature. Now, when looking at factors, we decided outdoor temperature is the primary factor that influences indoor temperature. And so as avid physics students, we decided to go for a differential equation model based on Fourier's law of heat conduction. We also recognize that indoor appliances can lose energy due to inefficiencies. And this becomes an extra term in our differential equation, which looks like this.
So you can see the differential equation here and our table of variables. The first step in solving it is to put Q equals mct. And this is it's a partial first order differential equation. And using the method of integrating factors, we can solve it analytically, which is superior to a numerical solution for a range of reasons. And here's the solution we obtain. You can see we've got a constant K there, which is shorthand, and T0, which is our indoor temperature at the start of the day. So in addition to all of that, we also need some values for our constants and also some functions of time. So specific heat capacity of air is just a constant, so that's nice and easy. Mass of air inside the building, that's the square footage of the building multiplied by the height of the average room multiplied by the density of air. That's not so bad. For T0, temperature at the start of the day, I mean, we took room temperature for that, but you'll later see when we varied that in the sensitivity analysis, it almost has no impact at all, so it's not that important. But thermal transmittance, so we looked at the construction date of all the houses given, and that allows us to deduce a likely wall type, get our value. The wall area, we did a little bit of research, a little bit of random sampling here to find the quantities R and H, and then it's quite easy from there to find an equation for the total wall area. And then I of T, the power transfer due to inefficiencies in indoor appliances. So we profile the houses as high, medium, or low energy use. And this is according to the UK energy regulator. And then we break down this energy use. Again, this is average across the entire UK. And for each of these energy uses, we assign an efficiency. We also assign a time of day when these are likely to be used. And summing over all of these, we obtain a plot of I of T.
Now, the temperature data provided by M3 is in discrete hour intervals, but our model wants a continuous function as input. So we fit a continuous curve to the data using a truncated Fourier series, here consisting of 4 sine waves. And we fit this via gradient descent in the Desmos graphing calculator. So we initialize our fit with some random parameters here. Some we choose manually just to speed up training. And then each iteration, which was achieved using an action, we update each parameter by their gradients. Over time, the loss decreases and we get an increasingly good fit, which looks like this at the end. And this can now be plugged into our model. Also, shade can have an impact on the outdoor temperature. So in the data provided, each house was assigned a shade descriptor of either not at all shady, not very shady, somewhat shady. For each of these, we assign them a temperature drop. And then throughout the day, we scale that temperature drop by this kernel here to account for sunrise, sunset, etc.
And here's just an excerpt from our code. You can see our parameters there for each house. And I'll just draw your attention, not sure if you can see it, but at the bottom, we have the integration. That's using SciPy's function, which implements the Simpson rule. And this is verbatim exactly the equation that you saw earlier in the presentation. So here are our results for each of the 4 houses. Now, the first thing we thought when we saw this is, wow, that's a lot of degrees. But if you look carefully, you'll notice there's actually this letter F here. Apparently there's this thing called Fahrenheit. Anyway, after digging our equation books out, we managed to convert to Celsius, and it turns out, yes, it actually is a lot of degrees. We'll come on to why the values are so high later. But first, sensitivity analysis. So we varied T0, as mentioned earlier, and had no impact. We varied I of T, and this did have a significant impact, which is to be expected, given that this is it's a key contributor to the model. I would expect that. And then some brief advantages, disadvantages. Strong, flexible, high stability, all good things. The main disadvantage is this very high temperature value. Why is the temperature value so high? Well, the main thing we think is likely to be the cause of this is I of T being unrealistically high. And the good news is that because our model is so flexible, we could revise I of T, put in new I of T, and we'd get more reasonable results. I'll hand over now to Raj and Dev for question 2.
So now we'll present our solution to question 2, Power Hungry, where we modeled the peak electricity demands of Birmingham during the summer months. So just first, some assumptions that we made. We assumed that Birmingham's monthly electricity consumption and the UK's monthly electricity consumption would follow the same distribution. And we also assumed that trends in any complicating factors would remain steady. So just a brief overview of our model. Our model had 3 parts to it. Due to the poor availability of data for Birmingham's monthly electricity consumption compared to the UK's as a whole, which was much greater, we decided to model, the bulk of our model was designated to modeling the UK's national electricity consumption, with another model for Birmingham's contribution to this, and then finally a third model to correct the residuals of the previous models and better capture those spikes. So here you can see some of the variables that we took into account and just units for them. So starting off with our first model, which was used for finding modeling Birmingham's contribution, we just first started with an initial investigation, plotting the whole of the UK's and Birmingham's annual electricity consumption. And the trend was entirely non-obvious. So we also plotted Birmingham's contribution. And at first, it looks really erratic, but you may have noticed that the scale of the graph is quite misleading. And there isn't actually a very high range. So it is about constant. But anyway, we decided to go ahead and try 3 different models for this. And we eventually settled on the quadratic model because it has the minimal mean squared error. We fit these models using gradient descent in Python's sklearn. And one disadvantage of this, though, was that because it's a quadratic model, as t approaches infinity, it will just tend to negative infinity.
So now I'm going to be talking about model 2, which is kind of the bulk of the model. So if you see our plot on the left here, it's pretty clearly seasonal, as expected. And so therefore, after some research, we settled on a Holt-Winters model, which was implemented in Python's stats models. So a Holt-Winters has 3 components: the level component, the trend, and the seasonal. And so there are 2 parameters, additive or multiplicative, in terms of the trend and seasonal components. And because there were only a small number of combinations, we just decided to test all of them. And so we ended up having 2 multiplicative components with the least mean squared error. And this is the model that we fit. The equations there on the left, you'll see that L sub t is level, B sub t is trend, and the S sub t is seasonal. And so we were pretty impressed by this. It looks pretty good. But there is one hair in the soup. And it's these little blue spikes. And so when you want peak electricity demand, you always want to err on the side of caution. And so we wanted to kind of capture these spikes a little bit better. And so that leads me on to model 3. But first, I'm going to talk a little bit about our technical implementation of the code. And so here you can just see we loop over all possible combinations of additive and multiplicative, and we find the one with the least mean squared. And so here's model 3. To make sure we weren't having some kind of delusion, we wanted some kind of objective metric to determine how much we were misrepresenting these spikes. And so after some research, we settled on a forecast bias. Here we've called it a peak demand bias. And we just examined the most extreme values and see how they compare to the rest of the data. And so we had a systematic underestimation. And here's just the calculation for that. And you can see at the top that it's just the top 10%. So here's the model 3. Well, first we plot the data. It looks pretty random. It looks pretty meaningless. But if you ignore the scale of the amplitudes of the graph, you can see it's kind of on the time scale of about 6 months is the period, which coincides with the seasons. And therefore, that leads me onto our first option for model 3. Linear regression with Fourier terms to better capture seasonality. And this T here is average maximum temperature, which we've normalized. And we decided to raise it to some powers to kind of emphasize those extreme values. The justification for this is as follows. We think that when you have more extreme temperatures, you're going to be more likely to use things like air conditioning and heating. And these are pretty big users of electricity. These are used a lot of power. As you can see then on the left, our eventual combined model, which we think looks pretty good. And here's our second model in just a sec, but here's just the implementation for that. You can see this function down below just loops over a certain number. We can just select the number of terms, and then we looped over up to a large number of terms and found the one with the least mean squared error. So here's our second option for model 3. We just followed standard advice on selecting parameters for a seasonal Aramat model. And so you can see here the autocorrelation function plots and the partial autocorrelation function plots. And so here was this model, the fit. You can kind of see it's a bit similar. The graphs aren't huge, but you'll see also it kind of moves away from how it originally used to match. And so you'll see that captured in the figures here. The mean squared error for the Sarima is actually significantly worse than the regression, and the peak demand bias didn't even really improve. And so unanimously, we picked the regression model. And so here are our results. You'll notice one little thing. Earlier, I talked about temperature influencing the results a lot, but quite curiously, in the summer months, the consumption actually goes down. And the reason for this is that in the UK, we don't really have air conditioners. Very few homes have air conditioning. And so a lot of, I know Americans find it funny when we call 15 degrees Celsius hot or 20 degrees Celsius hot, but our homes are built to capture heat. 20 degrees Celsius is proper shorts weather, lounge on the lawn, get a suntan weather. So yeah, that's why it's actually decreased. And now onto the sensitivity analysis. We decided to only do this on the second model because it was just the most important. And you'll see it's pretty stable on the small variations.
Yeah, so I'll just be going through the evaluation now. We thought our main disadvantage was the fact that this isn't feasible in the long term because of Model 1, as I mentioned, but our main advantage was its modularity. So it is actually quite flexible. We can fix the whole model with little effort by just adjusting our first model, and then it should still be feasible in the long term. Now I'll be handing over to Dewey and Arian for question 3.
So question 3 was about calculating a vulnerability score to power outages and heat waves for neighborhoods in Birmingham. So the assumptions. The assumptions were mostly made due to insufficient data and to avoid overcomplication. I'll gloss over that. Our rationale. So we had 2 potential approaches. The first approach was to use a normalization function, so to put each factor through a normalization function and then sum them up. We decided that this would be just difficult to justify which normalization function to use. So we considered using approach 2, which was ranking each factor and summing the total ranks. And the advantage of this is that it's more versatile when comparing the neighborhoods in Birmingham. Sorry. I also would like to say that it would have been great to consider, we really wanted to use k-means clustering, but if we had more time and more data, that would be much more.
Here are the 5 factors which we considered: 2 for power outages and 3 for heat waves. For these factors we won't consider because they're difficult to quantify and data is incomplete. So for energy consumption, we could look at the total consumption, but we decided looking at each individual's electricity usage is a better indicator of how dependent they are on electricity. So this is calculated by dividing that by the population. And then for vulnerable jobs, we look at the proportion of jobs that are in vulnerable industries. So we just sum up the number of jobs in those, divide that by the total number of jobs to obtain this ratio. I'll hand over to Oliver and Raj.
Okay, so on to the heatwave related stuff. So first we have the work and education risk. So we split jobs here into high risk, medium risk, and low risk with respect to heat waves. And we weight them 100, 10, 1 logarithmically. There's some justification there. Then for transit related risk, we wanted to encapsulate the density of individuals on transport because the denser, the warmer, and the warmer, the higher the risk of heat stroke, etc. And this ratio here, you can see N and S, how they're defined, encapsulates that.
And now onto leisure related risk. So here we just kind of have 3 factors. Basically, how much green space is there for you to cool off? How much space is there for you for designated areas for you to cool off? And how close are you to get drinking water? And then we don't have really any feasible way to compare how important these are. And so we just take the default position of weighting them equally.
And then finally, we also wanted to encapsulate the fact that higher temperature means higher risk everywhere. So we got a lot of data for excess deaths and temperature during heat waves in summers. And we did a quadratic fit. By quadratic, well, it makes sense that if you're already at a high temperature, the same increase in temperature will be even worse than if you'd started low. You can see the fit has a very low R-squared. It's important to understand that when you're putting in the temperature, you're not actually calculating excess deaths. We're just calculating a multiplier that represents the increased risk. We multiply through our raw values by these.
I want to ask a high level question because you noticed something interesting in the data, which was that in the US, like in the summer months, the electricity use goes up, and it seems like that's not the case from Birmingham. And I think you attributed that to the lack of air conditioners. So taking a step back from like all the modeling you did, is Birmingham at risk for heat waves? Is it a problem we should be worried about? Is the fact that there are no ACs telling us that it's not an issue, or is it saying maybe it's less prepared? What's your takeaway from the modeling you did?
Yeah, Birmingham in particular has quite a lot of office blocks, and it is really at risk of heat waves because like it kind of functions as an urban heat island. Everything basically traps heat and there's no way to get rid of it. And as like kind of climate change gets worse and temperatures increase even just slightly, it gets even worse. And air conditioning, especially in the older buildings in Birmingham, can't really be installed. And Birmingham's not a very wealthy area in general, and so air conditioning is unlikely to kind of make a presence there. So yeah, it is really at risk of heat waves in particular.
Okay, great, thanks.
Can I just add,
Yeah, go for it.
based on British weather, I wouldn't say it's as at risk as, say, Memphis in the US, but as a very urban city like London, definitely still has risk.
Thanks.
Okay, in number 2, you did a lot of modeling, a lot of coding, but could you comment on the average energy consumption in the future, like for the next 20 years? Any thoughts about that?
Yeah, so we didn't have a specific figure for that because of the first part of our model was very short term. And I guess we could have used a linear regression to like kind of assume that it does continue linearly and forecast into the long term. But I would say the trend is that it was decreasing pretty significantly. If you looked at the plot, the trend was decreasing. And this is likely to continue, but we can't really say with huge amounts of certainty because of things like innovation, also political changes like environmental initiatives.
Thank you, makes sense.
I have a question about your question 1. You acknowledged that the air temperature that you're predicting within the dwellings is higher than most. In your talk here, you focused on the I of T term. I was wondering, why did you focus on that, and what would you adjust?
Well, of the 2 terms we had, which were the heat conduction stuff and the IoT, the heat conduction is the one with the very strong, theoretical physical foundation. And there's no reason to believe that there would be anything wrong there. And in some simulations we did before we had added the I of T term, we found that the numbers were all very reasonable. For I of T being wrong, it's hard to say. Part of it could also be due to underestimation of the efficiencies of devices. So obviously nowadays efficiency is only increasing. And so it may be the case that we're overestimating heat loss there.
So I have one technical question, but I forgot. I wanted to comment. I have never seen gradient descent run in Desmos. I use Desmos for a lot of things, but that is new to me. So kudos on that.
Thank you.
For question 2, you use this Holtz-Winter's model, which it actually captures some seasonal effects, right? It can capture cyclicity in the data. And then I think you nicely observed that there were some errors in the model, some spiking errors, and you tried to account for that. But when you did that second accounting, you actually attributed those additional errors to seasonality. I didn't quite understand the story there, right? It felt like the original model should capture seasonality, and if the original model wasn't matching the data, there should be some other reason why. So can you explain that choice to correct those errors with another model that was trying to capture seasonality?
Yeah, both of them kind of, it wasn't to correct any seasonality effect. It was just because the first model, obviously, because it will predict expected value. So it will systematically kind of always be away from any spikes. And so that's, necessarily the other model had to be seasonal. Otherwise it would kind of just flatten out the seasonality into basically just like to make it more uniform. So I guess the second one kind of had to be seasonal as well.
So could you have, like, why, for example, use 2 different seasonality? Like you used I think a model with some fixed Fourier frequencies for your correction model and use this Holtz-Winter's for the first one. So why, could you have just corrected with the Holtz-Winter's model?
Yeah, we did actually try another Holtz-Winter's model, but it was just making it worse by like a lot.
Okay, makes sense.
So because you're a haberdasher's boys school, I have to ask about your outfit. What do the numbers on the back represent, or is it random?
Should we do a live demonstration?
Yes, do a live demonstration.
Okay. Okay, so let's see this. Okay, wait, can you? Oh! Wow. Thank you. I'm glad I asked then.
Okay, thanks. If you guys want to say a word of thanks to whoever, now's the time to do it.
So firstly, I'd like to thank our coach, Miss Harrison, and our chaperone, Mr. Broadwith, for their endless cheese jokes, public dances. It was great fun. I want to thank the twins' parents and Oliver's mum for giving us a place to stay for 14 hours and sheltering us from the harsh British weather. And finally, thank you to all those running this competition at M3, Siam, and Jane Street. And it's a wonderful opportunity. We really enjoyed New York, and thank you very much.
I just want to add one quick shout out to Mr. James Lee watching us from home. Thank you for your support, sir.
We have a 10-minute break now, I guess, or a little bit more than 10 minutes till 11 o'clock, but we'll be back here at sharp at 11 o'clock.
Thank you.
It was like, it was very nice.
Thank you.
Thank you.
How's everybody doing? Does anybody need any? Yes, I know where they are. We can go right out the door. The pink hallway. You couldn't see it? No. Yes, yes. It says pie. Oh, okay, so because I know everybody else got it.
Yeah. We couldn't block. I bet we can't.
Well, I'll tell you why all of this is because I thought that the videographer needed to have a shot. This is me. I thought.
That's why.
Yeah. But I think next year, just put you on the other side of this pole, push up, and I don't know, whoever sitting in gets the shaft every. Yes. Yeah. But the videographer, when I said this, he was like, I have my own hand. Like, well, that is even a whole. No, the screen was up, but much higher. They weren't like that was a game time call. They've all been pretty good sports about standing up. I was like walking over to them. We're getting ready to go, so. I don't know. I don't know what was. This will be new. It's not terrible for me. I got the best. The way. I think it'll be fine next year. Here, we could even angle. Oh, he is using that camera. Yeah, he uses that camera. But when he films you all, he's come over here. I like the. But I do try to capture this stuff. Right? Yeah, you were like, "Yeah, how did-"
Yeah, that's true. I forgot that.
Never that disappeared. I just be like, I gotta remember. And
Change it, you see? Next one coming. Okay, wait, what you're saying? What are you saying? The problem? No, it's. So this one is. Oh, no.
Okay. Okay, thank you.
Yeah, we're waiting on one judge, but we'll get started in a minute. Actually, yeah, if you are not presenting, if you can take your seats, because we'll get started shortly. Welcome. So we're going to get started in a minute. You'll have 15 minutes to present, and I'll give you a 5-minute warning, a 2-minute warning, and a 1-minute warning. So just glance at me occasionally. And then at the end, we'll have 5 minutes for questions and a minute for you guys to thank whoever you want to thank. So before you get started, if you could just all introduce yourselves and then begin, and I'll start the timer once you begin.
Okay, hi, I'm Katie and I'm a junior.
Hi, my name is Jerry. I'm a senior.
Hi, my name is Cole and I'm a senior.
Hi, my name is Victor and I'm a junior.
Hi, my name is Connor and I'm a junior.
Okay. Good morning, judges, guests, and everyone here today. Our team is from Trinity Preparatory School of Florida, and we are here to share our solution to the 2025 M3 Challenge hot button issue, staying cool as the world heats up. Various sources published these images illustrating the devastating effects of heat waves across multiple cities. These events lead to widespread power outages, serious health issues, and even death, particularly among vulnerable populations like the elderly, young children, and economically disadvantaged communities. To better understand and address this issue, our team has developed 3 key models. Today, we will discuss the steps we took to create these models, along with what we learned from each of them. We will also present our proposed solution to mitigate the impact of heat waves. Through our models and solutions, we hope to help inform government action to better prepare communities and alleviate the stress and harm of heat waves. Let's begin with the first question, which asked us to develop a model to predict the indoor temperature of any non-air conditioned dwelling in Memphis. To start, we decided on the following key assumptions. First, the primary drivers of heat gain are outside conditions such as outdoor temperature and solar radiation, and these conditions dominate internal heat gains caused by occupants or appliances. Second, dwellings remain closed with minimal ventilation and maintain the same thermal properties over time. Third, we assumed that the outdoor temperature of Memphis follows a smooth daily cycle represented by citywide data from a historical heat wave day. And last, we assumed that daily solar heat gains are approximately represented by a sinusoidal profile starting at sunrise, peaking at noon, and falling to zero at sunset.
Okay, thank you. Now on to our model selection and approach. So we chose to model heat transfer directly as this accounts for the time-dependent behavior typical of heating, such as lag and dampening, while also taking into account all of the dominant external factors present. Our model also allows for simplification since we treat the house as a single thermal zone with a uniform internal temperature, and we use a few aggregate parameters in a single ordinary differential equation to model the heat transfer. We initially also considered a time series approach like ARIMA, but we ultimately decided against it since we believe that the physics-based model had stronger explanatory power, meaningful parameters, and works when historical data may fail us or not be readily available. Now, here on the screen is our final model equation. I'll get into how we developed each of the parameters in the subsequent slides. Now, first for the UA value, which is the lumped thermal conductance. We determined that since UA varies with material, we would split the house into 3 key areas: the roof, the walls, and the windows. We calculated a value for each of them, and then we summed it up for a single aggregate parameter of 102.6 watts per Kelvin. Next, to determine the thermal capacitance, we used a common approximation, and then we used the 4 representative homes provided to determine a single floor area, and then we multiplied the 2 for our final C value. Next, to determine a function for the outdoor temperature over throughout the 24-hour period, we fitted a smooth curve using the provided data points, ensuring that the model generalized well. And finally, to obtain a function for the solar gain through windows throughout the day, we determined that the peak solar gain would be approximately 2.5 kilowatts. And then we used a sinusoidal approximation throughout the day with 6 a.m. as sunrise, where it starts from 0 and then falling again to 0 at sunset, 6 p.m. Now, here is our model execution and results. The indoor temperature, the predicted indoor temperature is represented with the blue curve. On the left is what it would look like throughout the first 24 hours of a heat wave. And on the right is the what it would look like over a consecutive 10-day period. And so we predict that the peak indoor temperature would be just shy of 36 degrees Celsius in the first 24 hours. Now, since there is uncertainty in estimation of our parameters, we conducted sensitivity analysis. We targeted UA and C values as their values within our control during the construction of homes, and we found that our model output remained relatively stable, even as we varied these parameters by up to 50%, not varying more than a few degrees. We also found that the thermal mass or capacitance is more than 5 times more influential than the UA value, and that homes are much more vulnerable to lost mass than it can benefit from additional mass. And finally, for a summary of our model, we modeled the heat transfer directly for good generalizability during extreme heat wave conditions when historical data may not be readily available or an accurate representation for future conditions. Our model is also easily interpretable and captures all of the critical physics-based dynamics and allows for rapid what-if studies as it's very computationally light, and we can potentially optimize UA and C value pairings during construction to minimize the indoor temperatures of dwellings. Now, as for weaknesses of our model, there will definitely be uncertainty in estimation of parameters, and we may have oversimplified model inputs, such as using a sinusoidal approximation for solar gain, and also omitting any internal gains.
Thank you, Jerry. For question 2, we were asked to develop a model to predict the peak electricity demand during the summer for the city power grid to prepare. So here are the key assumptions that we made for this question. First, temperature rise is gradual and can be approximated with historical trends. Second, there's no large grid scale changes in consumption behavior during the summer. Third, population growth will continue growing in a manner that closely follows the historical trends. So to develop our model, we first did an exploratory data analysis and we analyzed the problem. And the first thing that came up to our mind is a time series model. And in order to build a time series model, we'll have to speculate our data in the form of a stationarity test. And the stationary test that we used was augmented Dickey-Fuller test. A test for whether or not there's a unit root within the regression of our data. And stationarity means that there's a constant mean variance as well as autocorrelation in the data, and a statistically significant results which have a p-value of lower than 0.05 will result in the rejection of the null hypothesis that there is a unit root within the regression of the data, meaning that the data is stationary. After obtaining a p-value of lower than 0.05, we determined that a SARIMA model is best fit for our needs. So what is a SARIMA model? SARIMA model is composed of autoregressive and differencing and moving average components while combining the seasonal patterns that accounts for both long-term patterns and seasonal patterns. This is desirable because we can see the seasonal patterns within the temperature throughout the year, and we deem that it is the best fit of our demand. And yeah, so the way that we obtain the parameters of our SARIMA model is by using a Python package called PMD-ARIMA. It automatically finds the optimal parameters for our model, which is PDQ for regular patterns and capital PDQ for a seasonal pattern, as well as finding a seasonal lag of months. Okay, so after obtaining the parameters of 202 for regular patterns, as well as 101 for seasonal patterns with a 12-month lag, we are 95% confident that the peak electricity demand in 2045 during the summer is between approximately 0.86 and 1.07 billion kilowatts hour. Up to sensitivity analysis, we changed the years that we used to train the model from 5 years to 10 years to 15 years and evaluated the mean absolute percentage error from the baseline forecast that we have in a complete set of data that we train, the model that we train from the complete set of data. And this mean value ranges from as low as 1.55% to 11.64%, with a longer training data, meaning a lower May value, and with a shorter training data, generating a bigger May value. And this is intuitive because with smaller data set, the model will accumulate more errors throughout the forecast. So this is the discussion of our model. The strength of our model is that it is easy to implement, and it's also fast to implement using the Python package. And it is also easy to interpret with the parameters of the SARIMA model, and it accounts for the recurring patterns that happens throughout the year. And the weaknesses of our model is that the forecast accumulates the error as the time of forecast increases, and it also fails to account for the external covariates such as policy changes and economic changes.
All right, thank you very much, Cole. Yeah, so, okay, what? Wait. All right. Problem 3 asks us to generate vulnerability scores to help a city equitably allocate resources to minimize the effects of a heat wave or power grid failure in those respective areas. And also, question 3 also asks us to generate a single approach that incorporates these vulnerability scores in order to craft a city's approach to heat waves. So in order to do all of this, though, we must follow first a few key assumptions. We will have 5, and they will be as follows. All zip codes experience similar heat wave intensity, but the ability to cope will depend on varying socioeconomic, demographic, and environmental factors. And then our second will be the contribution of each zip code to a vulnerability score that it has is going to be linearly weighed. All neighborhoods will respond similarly to high temperatures in energy consumption, and then all areas will be of similar size to allow for accurate population density calculations. And then finally, the weights of each factor are based off of EPA, NCA, and CDC sources to ensure an accurate representation of the risk that each factor may possess.
Thank you, Victor. So continuing on question 3, because heat wave vulnerability is affected by a number of different factors, we used a multivariable linear equation to produce our vulnerability scores. Each variable is weighted and normalized based on its significance to heat wave vulnerability. This is to ensure an accurate scale of data is distributed to each factor in our equation. In addition, a random forest model was considered, but our group opted out of it after realizing the 27 zip codes we were given weren't good enough to generalize the data well. The potential model would also suffer from a lack of real-world data about how each neighborhood responds to heat waves, such as emergency room visits and blackouts. So each variable is normalized and given a specific weight. For instance, income and elderly population were weighted above the other variables in our equation. Notably, our model used inversely normalized components, such as open space, high income, and working population. The higher these values are, the lower the subsequent vulnerability score will be. The total sum of all these components give us a normalized score from 0 to 1, which gives us a data-driven comparative formula for decision makers to use. So the heat map we created breaks down each zip code from Memphis, Tennessee into normalized values from 0 to 1. Each cell in the heat map is normalized from 0 to 1, allowing us to compare the severity across multiple different factors graphed on the x-axis. The final column labeled total score represents the total aggregation of all the values. Darker red tones indicate a higher level of severity in terms of heat wave vulnerability. For a discussion of our model, some of the strengths are that experts can easily redefine weights based on different situations. It creates a clear visualization of the wealth disparity between Memphis, Tennessee cities, and it also is easy to interpret in policy situations. Some of the disadvantages are that it treats each factor as additive and doesn't account for the overlap. And it also doesn't learn from data patterns, and each factor remains static. Thank you.
As we previously mentioned, the 2 factors that we weighted the highest in our model were household income and elderly populations. From these guidelines, we determined that our solution must address these 2 key factors. The one solution approach that we suggest is the implementation of urban green corridors in Memphis, specifically in areas that are underprivileged and vulnerable to heat waves. There are 3 main impacts of urban corridors we would like to highlight. First, urban corridors will provide a cooling effect because of the trees that are planted. This will lift up household economic stability by lessening AC usage and therefore lessening electrical costs, while at the same time alleviating power grid usage. Second, trees will improve air quality and consequently improve elderly respiratory health, allowing for older residents to be less impacted by severe heat. And third, the aesthetic appeal of green corridors will improve property value, and this will in turn offer an increase in financial security for residents in areas where urban corridors are implemented. In conclusion, our team developed a dynamic thermal network model that predicts the temperature change inside a home without air conditioning, a SARIMA model that forecasts power grid demand during extreme heat, and a heat vulnerability map highlighting the areas most at risk. Thank you so much for your time, and we would now like to answer any questions.
Thank you very much. I wanted to ask about your vulnerability score. Can you pull up that linear equation? So one more, go back one. Right. So a couple of things, right? So your coefficients certainly sum up to 1, but like P is the total population, right?
Yes.
And that can be as big. What numbers did you see for P like?
Oh yeah, so this is population density normalized.
Okay.
Sorry.
Right. Yeah. So that's what I was going to get to, because certainly you have your 1 minus I over I max and the 1 minus over O max, right? And so you have that 0 to 1 factor, but right, P as you have it defined right now would not work, right? Because you don't really want the whole population to be multiplied by 0.2. It has to be a number between 0 and 1. So it should be population density as the definition. And then is there a similar redefining of E that you need to do as well?
Yeah, so every variable is normalized from 0 to 1. So does that answer your question?
Right, I guess the definition, so I should not, the definition of the variable should be changed a little bit there. And then there was a question from one of the other judges with regards to the median household income, right? I think the question was whether there should be an I-min or anything involved in that one. Do you want to say more, Kelly? I'm not sure. Yeah.
Yes, in terms of when you're trying to compare different neighborhoods and you look at your region, you have a minimum income and a maximum income. Yours only maps to 0 and 1 when the income is 0. And I was wondering if you could comment on whether or not you should incorporate
yes,
the
yeah,
minimum.
sure. So in our calculation of I and I max, for example, the wealthiest zip code would be I max over I max. So that would be 1. And so it would contribute 0 to the vulnerability score. And also, for example, the lowest income zip code you're right, yes. So I would essentially be 0 in our calculations. So this was based on like a relative ranking of the incomes in each zip code. Yeah.
Right, but maybe you didn't come across maybe a neighborhood that had 0 median income of 0, anything like that, but you would
no.
somehow,
The actual value, of course, was not 0, but in the relative ranking, it would be 0.
Okay. And then I don't know if we missed this, but could you say a little bit of how you came up with those various weights? Can you say that again?
Yeah, so for the weights, we used a lot of verified sources. Yeah, so we have the sources listed, and we basically just read up on literature and
Yeah, so we derived our sources from the EPA, NCA, and CDC, which are pretty reputable sources, and we did a lot of reading on literature provided by them and just their general importance to areas. And I think it's pretty straightforward that low-income residents may not have the means to respond to heat waves or have any access to like resources. Same thing with elderly populations, as they are not working and do not have the ability or means to.
I also want to add a quick note that our model allows for like very easy manual recalibration of each of the weights. And so we determined this ourselves, but of course, experts in the field, when governments are like making their policy decisions, they can contribute in on what they feel the weights should more like accurately be. Yes.
But these are the weights from your reading. These are the weights that you chose,
Yep,
right?
yes.
Okay. My question is back to question 1, part 1 of the challenge. It seems like you used outside data on home insulation coefficients as a function of home age. Could you elaborate on this? How did you collect the data? How did you create those models?
Yes. Okay. So what we actually did is we understood that U values would tend to vary with the time period that the homes were built in, just simply due to the different materials used. But however, since we wanted to develop a single model for all dwellings in Memphis, Tennessee, we tended to just we differentiated by the component of the house instead. So for example, we had a single U value for the roof and the windows, and we derived those from literature. Yeah.
Could you cite any sources? Are those the same sources as before, CDC and all that? Or you use something else?
No, they're not sources from the CDC, but they were taken from construction websites. So for example, the ones for walls would be like wood, like windows would be for the U values for glass and so on. Yeah.
Yeah, thank you.
One really quick question about question 2. So for question 2, you had this time series model which predicted electricity demand. I noticed can you go to the picture if you don't mind? I noticed your predicted, keep going to the actual plot. Yeah, here. Like if you look at top bottom right picture, your predicted demand seemingly for like all years is below like maybe half of the maximum demand from the previous years. And I'm wondering if you could comment on this. Like it seems like it's a believable trend maybe as like an average electricity use, but given that you're trying to predict a maximum, how could this model have been adjusted, or would it have been adjusted to better capture the max?
Okay, so this image might not be entirely clear with the white background, but we do have a 95% confidence interval within that predicted area. Like, so it varies up to here. It's a little bit too light, the color, so you couldn't quite see it. But it does vary up to like quite a lot, like compared to the dark red area. So
okay,
yeah.
Yeah, I think I literally just don't see it, but I'll look more closely on
the
that.
coloring is a little bit off. Yeah.
Okay, awesome. Thanks, guys. And if your rep wants to say a few words of thanks, now's the time to do it.
Our team would like to thank all the people who helped us reach this point today. So first and foremost, we would like to thank our coach, Mr. Worcester, for putting this team together and preparing us for the challenge. We would also like to thank Mr. McJimsey for chaperoning this trip to New York. In addition, we would all like to thank our families for their unwavering support and encouragement throughout this process. And lastly, we would like to thank Jane Street, CM, and MathWorks for putting this challenge together and hosting us today.
Thank you.
Thank you. Thank you. Just wanted to make sure. Okay, that's perfect.
Is it good?
Yes, thank you.
Okay, welcome. We're gonna get started in a minute. You have 15 minutes to present. I'll give you a 5-minute, a 2-minute, and a 1-minute warning. So just keep an eye on my markers. We ask that you begin by just each introducing yourselves, and then once you're done, begin whenever you're ready, and I'll start the timer.
Okay, thank you.
Thanks.
So, all right. Welcome, judges, competitors, and guests. My name is Jessica Young.
I'm Grace Law.
I'm Stephen Gu. I'm Brandon Willoughby. I'm Brandon Yang, and to make it simple, we're all seniors.
And we are from the North Carolina School of Science and Math, and we are presenting on the hot button issue, staying cool as the world heats up. Heat waves are deadly, but unequally deadly. Heat waves have devastating impacts on people's mental and physical health and could lead to death. In fact, according to the EPA, over 1,300 people every year in the United States die due to heat-related reasons. And these numbers will continue to rise as temperatures rise. Within these numbers, we found that certain communities are disproportionately affected. Thus, the equitable distribution of funds could save countless lives. So for our first model, we wanted to know how temperature changes within a house without AC for the first 24 hours to determine which kinds of houses are most susceptible to heat waves. So we have 3 major assumptions. Number 1, the initial starting temperature is 78 degrees Fahrenheit. We got this from the Memphis Light, Gas, and Water Division on the most energy efficient temperature. Second, all units are rectangular for simplicity, and the number of rooms inside a unit is irrelevant since the system is a house, and thus whatever's happening inside the house isn't too important. And third, the proportions of households before 1950s is negligible. This is because the MathWorks data given to us is from 1950s to present day 2024. And speaking of data, we have 4 major points that we care about, which is number of stories, units and structures, size of unit, and then the year the house was built.
So we're also given data on what the temperatures are in Memphis during a 24-hour period during a heat wave. And our team decided to use Newton's law of heating and cooling to determine the temperature inside of a house during these 24 hours. But first, we had to find the heating and cooling constant K, which depends on 5 main parameters, 2 of which are thermal conductivity and specific heat capacity, which both depend on the house material. Our team wasn't able to find enough information on how house materials changed from 1950 until the present. So, except we knew that houses were mainly made out of brick in the past and now are made out of wood. So we made the assumption that in 1950, houses are made entirely of brick, and in the present, houses are made entirely of wood. And as time increases, the percentage of the house made of brick decreases linearly. We're also interested in A, which stands for the air exposed surface area, as well as M, the mass of the house, and D, which represents the thickness of the exterior walls, which we're assuming is going to be 0.2 meters. So using our linear gradient concept, we come up with the two formulas in the top for thermal conductivity and specific heat capacity. As for the exposed surface area, that's equal to the number of exposed sides E multiplied by the dimension of each unit, which is L. And then finally, for the mass of the house, that's equal to the density of air multiplied by the volume of the house, where volume is just the height, which we're assuming is going to be 9 feet, multiplied by the dimension of the unit, which is L. So now using these the four inputs that Jessica talked about, our model will output graphs showing indoor temperature, which are the blue dots, versus outdoor temperature, which are the orange dots. And we decided to show this for 5 full days because the indoor temperature doesn't equilibrate to the outdoor temperature in just 24 hours. And as you can see, we're mainly concerned with the rate at which the indoor temperature equilibrates to the outdoor temperature, because that's what sets these 4 graphs apart, which show the temperatures for houses 1 through 4. So now I'm going to conduct a sensitivity analysis. On the left is the graph showing indoor versus outdoor temperature for house 1. And on the right, we're changing each of the 4 input parameters slightly to see how the blue curve, which is the indoor temperature, changes. As you can see, our model is very robust when it comes to increasing and decreasing the dimension of the unit, which is shown in the top right. And then that's because the blue curve doesn't change much. Our model also shows that houses that are built later are much better at insulating because the temperatures decrease drastically, and also there's less variability in the temperature, and that's shown in the bottom right. The main strength of our model is that we have visual graphs, so it's easy to compare indoor versus outdoor temperature, and we're also showing this for 5 whole days, so you can understand the relationship between those temperature values. And however, the main weakness of our model is the linear gradient concept. Obviously, building practices change discretely, and we tried to model this continuously. And so that was the best we could do. And we're also not sure if the M in our formula stood for the mass of air, the mass of the house, or both. So we just assumed it was the mass of air.
So moving on, with heat waves also comes an increase in AC usage, which can often lead to the power grid overloading. So that's why in part 2, we're going to model the peak energy demand in Memphis for the summer months and how this might change in 20 years from now. So we began by assuming that our selected sectors encompass all electricity consumption, meaning that no other sectors contribute. Secondly, we assume that no unpredictable factors such as sudden economic policy change or natural disasters affect our regression models because they're simply too unpredictable. And thirdly, we made the assumption that Memphis's peak energy demand can be modeled as a proportion of Tennessee's peak energy demand. While this might leave certain sectors like residential underrepresented because Memphis is an urban area, we did not have enough data regarding Memphis specifically to reliably do our model. So we began by splitting demand into 2 parts, demand from cooling and demand not from cooling. So demand from cooling is a function of temperature, which itself is a function of time. The demand not from cooling is a sum of each sector's energy times a constant K that represents how much is not used for cooling. So here are our regressions for each sector. As you can see, we use logarithmic for residential and commercial, which kind of shows a slowing growth rate in accordance with Memphis's slowing population growth. We used a bell curve for the industrial sector to kind of capture an upward and downward trend while still maintaining a horizontal asymptotic floor behavior so that it doesn't go negative. As you can see, the decrease in industrial will be so, later on we'll see that the decrease in industrial will be so great that despite the increase in the other sector's energy consumption, the total energy will decrease for Memphis in 20 years. So to determine temperature as a function of time, we've a sinusoidal regression to local Memphis weather data. And then we also tried to add a linear component to account for climate change, but it was not very significant.
So next we need to predict cooling, energy consumption from cooling, and we found this to be a proportion times the total peak demand. And we found this constant by dividing the total electricity consumption for cooling in Tennessee by the total electricity consumption in Tennessee. So next, we ran a regression to determine energy consumption from cooling as a function of temperature. And we found this to be, we chose a quadratic regression because we thought that at moderate temperatures that the energy consumption from cooling would be lower. And as you increase or decrease temperature, that the energy consumption would increase. And after this, we plugged in our temperature regression from earlier to get energy consumption from cooling as a function of time. So next, we predicted results in 2025 and in 2045. And we found that there was about a 10,000 megawatt hour decrease in the peak demand, which can be primarily attributed to the decrease, a projected decrease in the industrial sector. And this suggests that if Memphis is currently able to handle peak demands, that will likely be able to handle peak demands in the upcoming years. Next, we ran a sensitivity analysis by varying temperature from 82 degrees Fahrenheit to 94 degrees Fahrenheit. We found that for every 1 degree increase in temperature, there's about a 2% increase in energy used for cooling. Our main strength of our model is that we took into account each sector separately and ran independent regressions on those. And all of our data was, almost all of our data was sourced from the EIA, which ensures consistency in our data. But the primary weakness was the over-reliance on regressions. Our temperature regression was quite crude, and it's quite hard to predict peak temperatures, especially 20 years in the future.
All right, and part 3 asks us to beat the heat. Our goal is to develop a quantitative vulnerability score to determine the most at-risk neighborhoods and develop a funding allocation plan to help those at-risk communities. So our team created the vulnerability score V for all 27 of Memphis's neighborhoods. Note that this score is on the range from 0 to 1, where 0 represents a community that is not at risk and 1 represents the community that is the most at risk. Our team ultimately decided that only 5 parameters would play into determining the vulnerability of the community. The first one is the average income of all working residents. We'll call that I, and that's an inverse relationship to V, because if the community is generally more affluent, then they can invest in more quality HVAC systems. The next is the dependency ratio E, which in a human geography sense is the people over 65 and under 18 over the total population, so the elderly and the children. And that's a direct relationship because while everyone is vulnerable to heat waves, the elderly and children are especially vulnerable. So that drives up the vulnerability of the community. The third is the percent of adults with cars. We'll call that C, and that's also an inverse relationship because if more adults have access to cars, then they can get away from the heat waves if needed. The fourth is the average age of the house. We'll call that Y. Note that this is calculated by 2024 minus the year that the house was built. And as we've shown in Model 1, that's a direct relationship because older houses tend to have more poor insulation, which lets in more heat. The last one, which we'll directly use Model 1 for, is the average temperature in the house. We'll call that T. And keep in mind that that is the acute period when power grids are down and there is no HVAC system in the house. And that's a direct relationship. So with all 5 of these parameters considered, we have the formula in the bottom left. And the last step involves using min-max normalization to normalize the scores. The largest value for V we get, we set to be 1, and the smallest value of V we get, we set to be 0.
So I'm going to quickly revisit Model 1 because we're going to use that Model 3. So in Model 1, we had 4 inputs: the year that the house is built, the number of units in the house, the number of stories in the house, and the dimension of each unit. And then our model spit out a graph showing indoor versus outdoor temperature during the first 5 days of the heat wave. So we can find the average temperature in that house by just taking the average of those blue dots. And we're going to use that to help us with Model 3. But first, we have to make a few assumptions about these house types. We're going to assume that a detached home is made of 1 unit, 2 stories, and has a size of 200 square meters, and make similar assumptions for the other 3 house types. Now we're ready to calculate the average temperature of a house in a given neighborhood. And I'm going to do a sample calculation for South Memphis. So the first step is to find the average year that a house is built in that given neighborhood. And for South Memphis, that's 1957. And we can find that by just easily manipulating the data given to us. The second step is to find the average temperature given a certain house type in South Memphis. There's 4 house types, and we're going to use Model 1 to calculate the average temperature by plugging in the year 1957 and the 3 values that we made assumptions about on the previous slide. The final step is to find the average temperature given any house type in South Memphis. And that's going to be a weighted average of our 4 temperature values depending on how many houses in South Memphis are detached homes versus townhouses, etc. So you can see that the average temperature of any house in South Memphis is going to be 88.7 degrees Fahrenheit. Now we're able to create vulnerability scores for each of the 27 neighborhoods in Memphis. And as you can see, South Memphis is the most vulnerable neighborhood with a score of 1. As for the funding plan, it's actually quite simple. Our team decided to allocate funding proportionally with the vulnerability score. So let's assume that Memphis has $10 million to spend in funding. Well, then South Memphis would receive 10 million times their vulnerability score 1 divided by the sum of all the vulnerability scores, which is 8.038, which comes out to be $1.2 million. As for Piperton, which was the least vulnerable neighborhood according to our model, they get $0 because their score was 0. The main strength of our model are the normalized vulnerability scores and also how we use model 1. As for the weaknesses, we weighted all of the parameters the same in our vulnerability score formula. And that's because we tried to do some like scalar weighting, but that just went away after we normalized. Okay, I'm going to quickly summarize our entire project. So in model 1, we use Newton's law of heating and cooling to create graphs showing indoor versus outdoor temperature for 5 full days. In model 2, we split up energy demand by sector and ran regressions on each of those independently. And then in model 3, we created a normalized vulnerability score using model 1 and then created a funding plan accordingly. As you can see, model 2 was more informative for government officials, while model 1 was more useful in helping us create model 3. We would like to thank MathWorks and Science for giving us this amazing opportunity to compete, and thanks so much for listening.
Okay, my question is about your part 1, specifically about those 5 days, how the temperatures go up and never go down. Does it change the model in the long run? And what are your justification for 5 days explicitly?
Okay, hold on, let me just go to that slide. So we showed it for 5 full days because we thought that just showing 1 day didn't do the model justice. It didn't show how, like when the indoor temperature will equilibrate to the outdoor temperature. And because what we're more concerned about is the rate at which that equilibration like occurs, because we want it to be as low as possible.
Do you have any estimation when the temperature may go down to the initial temperature?
Well, I think like it's more visual. So it's like, as you can see in this bottom one, like it equilibrates much faster.
Yes, I can see that, but eventually it should go down to the initial temperature, isn't it? What if heat wave is longer than 2 days or 5 days? Would it change the model?
Oh yeah, we're assuming that the heat wave is going to go for more than 5 days.
Oh, more than 5 days, you said?
Because like the outdoor temperature is directly from the heat wave like data.
Okay, all right, thank you.
Yeah, I have a question about your vulnerability score. Just want to ask if you could comment on why you decided that particular form, why multiply instead of maybe add or subtract?
Yeah, so while we were looking for parameters, if you want to go, yeah. So while we were looking for these parameters, we're trying to determine the relationship of each of them to the vulnerability, because most of these scores, if it's higher, then the vulnerability will go down, or if it's direct, then a higher dependency ratio means that it's going to be more vulnerable. And so with a bunch of inverse and direct relationships, that just naturally led us to think that, okay, maybe we can multiply some of them and then divide it by the ones that lower the vulnerability, the higher they are, the inverse ones. And so that's what led us to the multiplication and division, although we did think about, we didn't really consider another formula for the vulnerability.
Just to follow up on that, so in terms of that form, one particular increase in the age of the structures has the same impact as an increase in temperature. I guess what's your reaction to that, and what might you do to try to make up for something like that?
Yeah, so while we were creating this, actually, we realized that a lot of the parameters had overlap. Like, for example, the percentage of adults with cars is almost certainly going to correspond with the average income in the neighborhood. And so we wanted to reduce it from the 20 something parameters that were given in the data sheet to as few as possible. And we probably could have gone further, but also we didn't especially want to reduce it to just 1 or 2 parameters because we felt like that would be an oversimplification. And so we just stuck with these 5. And then this last parameter also gave us an excuse to use our first model because we had that worked out. So we wanted to use it here.
And that's good. It's an important part. But just in terms of the impact, right? So what a corresponding increase in age of structures versus corresponding increase in the temperature, why should that hit the same way?
Yeah, so we were actually trying to solve this in the challenge. We wanted to say like maybe like income is twice as important as like dependency ratio, right? But that factor 2 just like goes away when you normalize. So next time we wanted to like maybe add like if we did some addition instead, then it wouldn't go away when we normalize. So if we were to do this again, we would take things like that into account.
I think another thing is there may be other ways to add in weights. Like you can use exponential factors, then that wouldn't go away in quite the same way. Because I agree, if you just did a linear weight, yeah. Can I ask a quick question about problem 2? So like for question 2, you had this nice curve where you plotted energy consumption versus temperature.
Oh, this one?
Yeah, what was the date? Can you just explain where the data came from? Like what were we fitting here?
So basically we had energy usage for certain years, like let's say like I don't remember the exact time frame, but like 1990 to 2024.
Okay.
And then we also had the temperature, like the temperature for those years. So we just like fit them against each other.
So you sort of like you threw all the years into one plot and then did a fit? Okay. Okay, that's all I wanted to ask. Okay, I think we're good then. Thanks, guys.
Thank you.
Yeah, if you want to thank anyone, you have a minute to do that now.
Okay, yeah. First of all, we'd like to thank our coaches, Dr. Teague, who's probably watching from North Carolina. Thank you so much for all your support. And also Dr. Levine and Dr. Tharp for coming on this trip with us. We'd also like to thank everyone who helped us come this far, our parents, our friends, and other math teachers as well. And yeah, last but not least, we'd like to thank our school, North Carolina School of Science and Math, for giving us this amazing opportunity to compete. Thanks so much.
Okay, thank you.
Is it one
the person
person?
who's speaking.
I'll tell everybody. In this presentation,
Okay, we're gonna get started in a second. It's a 15-minute presentation. You just have 15 minutes. I'll give you a 5-minute, a 2-minute, and a 1-minute warning. So just glance over to me occasionally so you don't miss those. At the end, we'll have 5 minutes for questions, and you'll have a moment to thank anyone you want. When you begin, we just ask that each of you introduce yourself, and then once you start the talk, I'll start the timer. So yeah, we can begin whenever you're ready.
Hi, we're team 17781 from Winchester College. I'm Victor.
I'm Alex. I'm Andre.
And we also have 2 members that couldn't make it because of visa issues. They're Henry and Yu Yao. Yeah. Before we get into the main content of the presentation, I'd just like to mention some of the unique contributions that our team brings. I think uniquely, we believe that mathematical modeling should be used to make mitigation strategies. So I think that we actually use technical computing to come up with very specific mitigation methods later in the presentation. We achieve this by data quantity, considering 3 separate sources of data, which each contain many of data points which would not be able to be considered without a tool like Python. And by data diversity, we mean like this type of data that is present means that we couldn't do it by hand or by Excel because it wouldn't be possible to clean and process this data otherwise. And by optimization, I mean, we consider the like computational complexity, like the NP hardness of the problem, as well as running multiple simulations such that we have a reasonably good solution. Also, when we mention scalability, we talk about the modularity of our code, which means that simple tweaks can mean that similar methodology can work in different systems. So now when presenting question 1 hot to go, this problem asks us to predict the indoor temperature given the outdoor temperature on the hottest day in Memphis, Tennessee. The method that we decided to use was Newton's law of cooling. Simply put, it describes a transfer of heat between 2 mediums over time and is basically characterized by a constant K, which we later determined to be specific to individual buildings. Why should we use Newton's cooling law? Firstly, we believe that physical principles are universal. This means that even though we use a UK data set for our temperature data, we think that physical principles hold the same anywhere. Therefore, any of the conclusions that we come to are valid. Secondly, it's more justified than only using a model which uses parameters. This is because we can use coefficients to explain what's happening, not just model the data. We think passive transfer naturally lends itself well to Newton's cooling as per physics principles. And also we think that since we're directly accounting with thermal energy and temperature is adjustable for human impact. The factors we included were the change in environment temperature, the human power output registered to be 100 watts as per literature review, as well as building-specific constants, specifically affecting K by volume and surface area. We did not account for effects of windows and ventilation as this was not given in the M3 dataset. To determine K, we basically split the data that, from a dataset into hour by hour levels and just rearrange Newton's cooling law in order to get a value for K. We averaged this across different rooms to get a reasonable approximation.
So to determine K, we used the Loughborough housing dataset. This is a collection of indoor and outdoor temperatures for a single family home, as well as a comprehensive floor plan, which we used to calculate the dimensions of the building. We used the temperature data in the dataset to determine K. We found that K is directly proportional to the surface area and inversely proportional to the volume. We then solved the system of equations to find alpha and beta, which generalized well across the data we used. We also found that the human power output was significant enough to change the temperature. We took this value to be 100 watts. Using the above physical laws, we found delta T, the change in temperature, which we will add to our final temperature. This code shows how we computed the temperature using Newton's cooling law. The key thing is that we did this by splitting into time segments and finding each individual temperature. Here you can see the computed temperature profiles for each building. Note that we used a standardized height of 5.51 meters. These graphs match the behavior we expected. The 4th room on the bottom right had the largest volume, and as you can see, it had the slowest heating. We also find that humans have a minor but non-negligible effect. We analyzed the sensitivity of our model both empirically and analytically. We rearranged Newton's cooling law on the left to obtain the below equation, and we found that the sensitivity decreases as Ts approaches Tt or T0. The figure on the right supports our hypothesis that K is highly sensitive to changes.
So the second question asked us to develop a model that predicts the peak demand that Memphis power grid should be prepared to handle.
So MLGW is the largest and effectively the only electricity supply in Memphis. On the left diagram, you can see that Tennessee Valley Authority produces most of its energy, which is then given to MLGW to distribute to its customers. This energy comprises effectively all energy used in Memphis, and therefore we can assume that MLGW is the only supplier of electricity, which means that we can use its financial reports to get the data about demand. On the right, you can see graphs for residential power usage and industrial power usage. We decided to take a look at power usage of different customers. And we noticed some fundamental differences between how residential and industrial units operate. Industrial facilities often have heavy duty of appliances on 24/7, whilst residential units often have energy use peak at different times of the year due to lighting and heating or cooling. This can be observed in the graphs on the right. Without splitting the data, our model would not account for seasonality in residential usage exclusively. So we decided to use Sarima and Holt-Winters models to model the demand. The study has shown that Holt-Winters model was superior at modeling less variable monthly flows, while Sarima models better forecast highly variable periods. So this is the data for our Sarima model. We predicted that summer and winter usages would follow different overall trends as time goes on. Using one Sarima for both winter and summer would merge two trends together or even kill one of the trends, which would greatly affect our final prediction for demand. Therefore, we decided to split data into summer and winter seasons and run both through corresponding Sarima models. So this is our Sarima model, and it takes 7 parameters. I'll explain how we chose all of the parameters. So first of all, we can straight away set S equal to 12 months or 1 year, as it's the length of the cycle. For values of P, D, and Q, we ran an augmented decoupleur test to determine a value of D, and we plotted partial autocorrelation functions and autocorrelation function in order to determine P and Q. As for seasonal components, we used an AutoArima library for seasonal parameters. So these are the results. As we can see, Memphis city residential power demand will follow a decreasing trend in the next 20 years. This was within our expectations because Memphis had a well-established trend of population decrease. Also, our model seems to discount the effects of global warming, but actually we believe that it's not the case because a decrease in population can counteract the effects of global warming in the summer, whilst effects of global warming are still present as it causes winter consumption to decrease.
So to model the industrial and commercial data set, we opted to use Holt-Winters exponential smoothing. This is effective when the data has a clear trend in seasonality, and notably more so than Sarima when there's less variation in the data. Here, you can see the variables we used, including alpha, beta, and gamma, which are constants which we will determine later. So Holt-Winters has 2 versions, additive and multiplicative. It was not necessary to test both to choose which one to use. We saw immediately that we should use the multiplicative version since the seasonal level scales with the overall level rather than staying constant. There are 4 equations involved in this. The level, this adjusts the base level. Our low choice of alpha here gives less weight to recent observations. The trend, this captured the long-term upwards or downward slope of the data. Our choice of beta here also gives more weight to the historic trend rather than recent anomalies. The seasonal, this updates seasonal patterns based on the ratio of actual to predicted value. Our very low choice of gamma here assumes a stable pattern throughout. The forecast equation uses the other 3 components to project future values. On the left, you can see a decomposition of our data into the trend, seasonal, and residual components. The trend suggests an upwards pattern, and our model on the right predicted this. We expect Memphis's ongoing industrial expansion to intensify, assuming the lack of a major climate change prevention. The results also captured the relative insulation of the sector from population decline, unlike the residential. To analyze the sensitivity of our model, we applied plus or minus 1% Gaussian noise and forecast for 20 years. This yielded an R-squared value of 0.9975. The fact that this is so close to 1 indicates that the model is resilient and precise. We also analyzed the residuals in 2 ways. Over time, on the left, they appear randomly distributed around 0. The fact that there's no visible pattern here is a strong indicator of model accuracy and lack of bias. As a histogram on the right, with an overlaid kernel density estimation, the distribution is centered near 0 and closely follows a normal distribution. This really confirms the absence of systematic error. Overall, our predictions for question 2 are shown. Although the residential energy usage will decrease over time, the industrial is clearly a dominating increase. As a city, Memphis's popularity in manufacturing and transport industries is growing, with many leading tech companies recently choosing it as the location for constructing huge manufacturing facilities, including a major new data center opened recently. So, the graph follows our reasoning that industrial and commercial power will increase and dominate. A major strength of the model is that by splitting the data up, we were able to expose separate trends, both for residential and commercial, by using the two different models. If we just modeled total energy usage directly, the trends we noticed would have cancelled each other out. This also allowed us to make separate predictions for residential and commercial, which would potentially be more useful in a real-world application. Now I'll hand over for question 3.
The question 3 tasks us with coming up with a vulnerability metric for neighborhoods in Memphis, Tennessee. The metric that we decided to go with was expected economic damage. Simply put, the expected economic damage of a neighborhood is the expected damage that a neighborhood would incur given a heat wave. We consider both the probability of a power outage as well as if a power outage doesn't actually happen. We later determined this to be dependent on certain grid features that we find. If there is a power outage, we expect transport networks to fail and the failure of network services in the neighborhood, and therefore the loss of the wages for all individuals within the neighborhood. If there isn't a power outage, we expect people to work from home as per CIPD data, and the main cost to be the cost of cooling. So now onto the considerations for a vulnerability metric. We think that the two main considerations for a vulnerability metric is to be policy ready and actionable. We think that policy ready means that it is easily understandable for non-expert policymakers. We think if we use a simplistic method like normalizing between 0 to 1, what does 5 mean, 1 to 10? What does 5 mean relative to 1? Is it 5 times worse, 50 times worse, or 500 times worse? In the case of in terms of economic damage, it's firstly immediately intuitive and visceral, and also you can easily compare the economic damage between two neighborhoods. Secondly, on being actionable. Later, we use this data to place emergency centers within Memphis, Tennessee to protect the most people. We think that economic metric is intrinsically linked to opportunity costs. Let's say an emergency center costs $2,000, but it could potentially protect $5,000 worth of economic damage. This helps government policymakers actually consider the weight of their actions and also to consider the optimal allocation which we will later present. So firstly, on determining the power outage probability, we focus on a small part of the grid of substations. Substations route electricity throughout areas, specifically neighborhoods in Memphis, Tennessee. And we think that the more substations there are, there's a lower probability of grid failure. From national grid research data, we get the working radius for each substation to be 2,000 meters. And from the same research, we also find and estimate the probability of outage to be between 0 to 0.3 and also linear to the number of substations based on MLGW historical outage data. In practice, we make an API query to the OpenStreetMap service, and we process each of them and add them to the map using the Python Folium library. Here are the calculated power outage probabilities. In terms of wages, we take a pretty simple approach and we find the average income that would be lost per person during a 6-hour outage duration. This is also gained from MLGW historical averages. We multiply this by the employed population and get the following results by neighborhood. Clearly, there is a very large range in the lost wages between neighborhoods. East Memphis will lose 1.68 million if there isn't a power outage, and South Forum will lose 115,000. The large range of values strongly motivates an optimized approach, as simply placing an emergency center next to each neighborhood would not adequately protect people, especially when we consider the resource constraints that the government deals with. In terms of calculating cooling costs, why should we model cooling costs? We think it's very important as it accounts for 40 to 60% of summer electricity bills, and it also encapsulates economic vulnerability. To do this, we basically adapt the model that we gain in question 1 and also add an HVAC term. In practice, this looks like adding an if-else statement that if the temperature is greater than 27 degrees, which we found from previous research to be the temperature at which Memphis residents begin to switch on their air conditioning units, that air conditioning unit switches on, which decreases the temperature. In practice, this looks like the temperature spiking down at certain points. And based on the amount of time that the air conditioning unit is switched on, we can calculate the cooling cost based on the cost of energy as per what we calculated in question 2. In terms of neighborhood vulnerability scores, we see quite a large variety. One would expect affluent neighborhoods to dominate the table, but we actually think that the most clear pattern is that the neighborhoods with the highest economic damage are those that are the most lived in. We actually think our metric protects the most people.
So we didn't actually stop at giving vulnerability scores because this does not tell the local government how to act. And we decided to develop an algorithm which will tell where to place emergency centers. So we're given the position of neighborhoods, E value, which is an expected economic damage, N, which is the number of emergency centers. We say that an emergency center is effective if it's placed within distance R from the city. We took R equal to 2 kilometers to be reasonable. Then we reduce the financial loss by 30%. if the emergency center is within the radius. This is a US Army power restoration statistics. Oh, you can see an example below. So now we will consider the points where a hypothetical emergency center can be placed. Drawing a circle of radius R around each town, we put one town in each region of overlap between two or more circles. For each circle, we also randomly place a point within it without overlaps. We do this using Shapley geometry model in Python. Then we simulate placing one emergency center at each of the points and compute the total score after placing this imaginary point. Then we place one which minimizes the sum at the current iteration. Then we update the total economic damage and repeat this process n times. Why is this algorithm good? It gives us near optimal placement in many cases. We suspect that the problem is NP-hard, similar to K-median problem, which is known to be NP-hard. So we think that we found the best solution that can run in reasonable amounts of time. It is important to know that by framing everything relative to the economic cost, we're aware of the government's resources. We then use technical computing to determine the best allocation. Our solution is also versatile, which makes it a good solution in terms of technical computing. So here are the results of our algorithm. As you can see, we have some emergency centers, and they are not placed in the most rich neighborhood, as one might expect. So they are actually equally distributed around the city, which looks reasonable and justifies our algorithm. That is the end of our presentation. Thank you very much for your attention.
I can start with the question. So I love the mapping you did for Q3, and I think you used it in two ways. One was like placing these centers, and then also this power substation thing. You were mapping number of power substations to probability of a power failure. Can you walk me through the link there a little bit more clearly? Like one thing you mentioned is some neighborhoods have more people than others. Actually, I think those were often your more vulnerable neighborhoods. So the number of substations like just a function of the number of people there? Isn't a meaningful metric for the chance of a power outage?
I think from a grid standpoint, like on a practical standpoint, the number of substations that are present definitely has a linear, like an effect on the power outage. And we did see in many cases that the number of substations that are present is also dependent on the number of people in the area. But we think that it's in residential neighborhoods that it's damaged, but substations may also be put to like protect businesses. And that actually results in damage to neighborhoods, especially because a lot of the areas with like bid rent are placed, like commercial areas won't be the same as the residential areas.
Okay. So if it could be that a power substation was placed because there's a big industrial area and that helps the surrounding neighborhood.
Yeah.
Okay, that makes sense. Thank you.
Yeah, I've got a couple questions about the vulnerability score, in particular around the calculation for lost wages.
Yeah.
So I'm in terms of power going out in a particular area, why does that necessarily mean that people there are going to lose wages and not work?
Oh, we expect the transport links to fail within that area, and those people would not be able to go to work. Of course, the alternative to that is working from home. But we think that if there is a power outage, networks would fail, and it wouldn't be sustainable for businesses to ask people to work from home if there is a power outage.
Okay, and then one to follow up there. In terms of lost wages, a more affluent area, you'd expect people to be making more wages and have a bigger vulnerability score because of that.
Yeah, I think we do concede this. I think part of the economic metric, obviously a drawback of this is that certain more affluent areas will take like a higher score because of higher wages. But we think this is a trade-off because what we actually result is that we can protect the most people. And I also think there's some other separate economic factors, which means that if general economic like wellness is maintained, it can actually benefit the rest of the city. That's another factor which isn't easily modeled, but I think it's a consequence of using economic metrics.
Okay, in part one of the challenge, you did mention a very interesting limitation that other teams didn't. The temperature likely is not uniform across the dwelling. So how would your model be adjusted to account for this limitation? Do you need more data? Would you include more variables? How would your model change?
Sure. So I guess we'd use we would need more data for the inside, and we would calculate the dimensions and also consider heat flow between different rooms. We could also have a gradient of temperature, but especially for high buildings, this would be useful. So we could have the temperature changing as you go up the building. So that would definitely be the things we would take into account.
Also, I think aspects such as wind speed is affected by several complex factors like houses in the vicinity and naturally the height. And this wouldn't really be possible.
Okay, yeah, thank you.
Well, nice presentation. In part two, you used the two different models, right? Did you actually implement a single model or try to approach for a single model at all?
Yeah, we did. So we tried to use the Surima model on the original time series, but we think that the lack of seasonality, because as shown, let me just give me a second. For the industrial section and the residential section, the seasonality is completely different. So when you add them together, it kind of cancels out in a sense. And so when we tried to do it, it didn't pass the test that we were given. And we thought intuitively they must follow different demands. So we tried to separate them. And once we did that, the trend was obvious.
I want to ask a follow-up question about that. Can you go to the plot that shows the trend for the industrial?
Or presentation.
Sorry, I know it's slow.
It means the slide with the left and
Or,
right.
no, I meant the one you would. I just saw it, but maybe I can explain it. It was the one where you're showing you show about 3 seasons of industrial data, and then you extrapolate out for the forward, and you have this strict increase, like a pretty steep increase in industrial usage. Keep going.
Whole winter's result.
No, keep going. Sorry, it's the next one.
Sorry, that's quite a lot of lag.
Forward. Yeah, I know, it's okay. This one. Okay, so to me, when I look at this data, if I just eyeball it, it looks like we're predicting a strong increase in usage off a relatively small amount of data. So I worry about the sensitivity of this model. Now, you did do a sensitivity analysis. You added some Gaussian noise, but you used a very small variance on that Gaussian noise. I think you said it was like a 1% of the magnitude or something. So I want to ask how you chose that variance. And say you were presenting this to I don't know, a decision maker who had to make decisions about this sort of stuff. How would you convince them this is a believable trend?
I think in terms of the Gaussian noise, I think it's relatively subjective to pick what the Gaussian noise value is. But I think potentially we could have fell victim to some kind of post hoc analysis because of things like data centers and current affairs effects that would promote higher industrial usage in the future. We might have been convinced that a high increase would be justified, but I do concede that the extent to which it will increase is kind of dependent on several other factors that we can't predict.
Okay, that's a good answer. Thanks, guys. So if you want to do a quick thank you, go for it.
Yeah, sure. I just wanted to say a quick thank you to everyone involved. So, I mean, firstly, team members, not only Victor and Andre, but also Henry and Yuya, who unfortunately weren't able to make it today. We're also extremely grateful to our school, Winchester College, and our coach for helping us and supporting us through every step of the journey. It's been great. And finally, to everyone involved in the organization of M3 Challenge, so Jane Street, the hosts, the judges, and everyone from SciAm for organizing this. It's been a great opportunity and a brilliant experience. So thank you for having us.
Okay, welcome. Your final presentation for the day. So you're gonna have 15 minutes to present. I'll give you a 5-minute, a 2-minute, and a 1-minute warning. And then at the end, we'll have about 5 minutes for questions, and you'll have a chance to thank your coaches or families or whoever you want to thank. So whenever you're ready, you can get started. We just ask that before you start the presentation, please introduce yourselves by name. And then when you start the actual presentation, I'll start the timer. Go ahead.
Hi, I'm Jack Dunn. I'm a senior.
Hi, I'm Divya Kudba. I'm a junior.
Hi, I'm Kevin. I'm a senior.
Hi, I'm Billy. I'm a senior. Hi, I'm Neve. I'm a senior.
And we're Team 17839 from Flint Hill School, and we are presenting our solution to the hot button issue, staying cool as the world heats up.
My team and I have two major worries. Our first concern is with the systemic threat that heat waves pose to urban residents across the United States. A report from NPR showed that less affluent neighborhoods of urban areas are disproportionately affected by heat waves. Additionally, a climate check risk report on Memphis, Tennessee predicts that by 2050, the city will experience 51 days per year with over 96-degree Fahrenheit temperatures. We've chosen the given data from Memphis to further understand the threat that heat waves pose to urban residents and to determine how to reduce the drastic impacts of climate inequality. The first problem asks us to develop a model to predict the indoor temperature of urban residences without AC. Our model is based on a few key assumptions. First, we established that the general approximation of a singular floor of a house is 10 feet. Another intuitive decision we made was that older houses have worse insulation, and that must be accounted for in our model. Third, we needed a standard value for air change rate of houses in Memphis, which represents the amount of times the air of a dwelling is replaced by outdoor air. I'll soon explain how this factor is used in our model. Our model considers thermal capacity, which we approximated to be 75,000 joules per Kelvin. Finally, we must assume that the heat source from the sun onto a housing unit is 3 degrees Celsius and only lasts from 6 a.m. to 6 p.m. Otherwise, this additional heat is 0 degrees Celsius. For our model, we decided upon a general energy balance equation. This will allow us to take into account several different sources of thermal energy using the data on dwellings in Memphis. In the form of a differential equation, we can solve for the rate of change of internal temperature of a housing unit. This easily allows us to model the temperature of a dwelling over a 24-hour period and thus allows us to estimate the effect of a heat wave on urban residences. This is the formula for the differential equation of an energy balance equation. We are able to define several sources of heat and utilize separate equations for each Q variable. One note, however, is that we eschewed Q solar from our final equation due to the fact that solar radiation was taken into account with our formula for Q conduction. I'll now explain how we calculate each individual variable. Our first consideration is heat from conduction. This formula uses Newton's law of cooling, which in this context means that the rate at which internal temperature of a house changes is proportional to the difference in outside and inside temperatures. The equation uses UA, the constant of insulation, which we determined from building types, with apartments having better heat transfer and houses having a worse. The TSA variable is solar air, which is the temperature outside plus a factor of solar radiation on the residence determined from the given shadiness qualities. Delta T simply enumerates the heat added from direct sunlight, thus why we scrapped a Q solar variable. Q internal is quite simple, in which we consider the number of people inside a residence and multiply that by the heat generated by a human at rest, which on average is 100 watts, relying on the assumption that all residents are within the house during this heat wave. Finally, Q ventilation determines heat gained or lost from circulation of outdoor air into the residences. We do so by considering an assumed rate of 3 air changes per hour, telling us at what rate indoor air is replaced. But this is our final differential equation for question 1, with the defined heat energy equations for Q conduction, Q internal, and Q ventilation implemented. Here are results with the graph showing the internal temperature of each of the 4 given residences over a 24-hour heat wave period, with the black dotted line showing the outside temperature in Memphis. Our findings show that home 2 was the most susceptible to the heat wave, peaking at over 42 degrees Celsius after sunset, primarily due to the old age of the unit, as well as the exposure to the sun. Our model suggests that smaller residences, like homes 1, 2, and 3, retain heat to a notable degree, with homes 2 and 3 having particularly high retention of heat due to being apartments with worse insulation, which would trap outdoor heat within the dwellings for a prolonged period of time. Despite both being apartments, Home 2 has a slower rate of cooling compared to Home 3, likely due to Home 2 being an older unit. Home 4, however, faces greater extremes in temperature as it is susceptible to rapid overheating due to the full exposure to solar radiation, as well as having a high occupancy of 6 residents. Our findings suggest that the location and shade, size of homes, and number of occupants are crucial factors to consider when determining risk for overheating. Our energy balance model is incredibly effective in capturing the rate of change for internal temperature. Since we must understand the rate of cooling and heating of residences, it's beneficial that this model takes into account instantaneous temperature. Additionally, this model is largely intuitive in that every part of our calculations has a logical explanation. Compared to neural networks, our model is by no means a black box process, which makes it easily applicable to real-world scenarios. Unfortunately, our model fails to take into account variance in weather. Factors like wind speed and sunniness certainly affect internal temperature, but could not effectively be incorporated into our model. Another shortcoming is in our calculations, in which using Euler's method led our data to be discontinuous. Thus, our data is only a close approximation to the actual solution. Additionally, in order to use Euler's method, we had to interpolate the given data from hours into seconds, which may hinder the accuracy of our model.
Problem 2 asks us to develop a model that predicts the peak power demand that Memphis, Tennessee's power grid should be prepared to handle during the summer months. It also asked us if we foresee any changes in the peak power demand 20 years from now. In order to tackle this problem, we had to make a few key assumptions. Our first assumption is that the average temperature people in Memphis keep their houses at is between 70 and 73 degrees Fahrenheit. Secondly, we assumed that air conditioning units have varied capacity factors based on age, as it is effective in capturing the rate of, as it reflects real world conditions where older AC systems experience reduced capacity due to outdated technology and improper sizing. Thirdly, we assumed that buildings have a single thermal zone, as is standard for city scale simulation. We also assumed that Memphis's housing stock can be represented by 4 archetypal building models, as considering all possible dwellings increases the complexity greatly. To tackle this problem, we decided to use a simulation model that utilizes our solution to question 1 to create a thermal equilibrium model. This simulation combines the power draw from dwellings due to air conditioning and a power baseline that accounts for appliances and other uses. To accurately model the entirety of the housing stock in Memphis, we created an age and type distributions for all the houses. The power baseline was created by averaging the power draw for the city of Memphis during the spring and fall months, as these months can be expected to have the least amount of air conditioning or heating usage. Building off our solution to question 1, we built a thermal equilibrium model quantifying the heat exchange between buildings and the environment. This approach offers an accurate citywide demand representation by calculating the energy required by a house to keep it at their desired temperature. Unlike statistical regression, our model captures nonlinear temperature-power relationships and accounts for crucial building-specific factors like insulation and AC efficiency, which historical data alone cannot provide. Our energy balance equation from question 1 tells us the amount of energy needed to keep a house at the set point. We then divide by a coefficient of performance for the AC unit, allowing us to relate it to the amount of energy it takes to cool the house to the energy increase inside the house. If this value exceeds the amount of energy the AC unit is rated for, the house's temperature increases, and the power consumed by the AC unit is the power it is rated for multiplied by the capacity factor. Our simulation consists of adding the baseline of powers to the sum power draw from each of the 4 archetypal dwellings with a scaling factor applied to account for industrial and commercial air conditioning. We then simulated a heat wave in Memphis, which showed a total power draw of roughly 2,850 megawatts, with 32.5% being from air conditioning. After running our simulation, we conducted a sensitivity analysis to determine what factors are most important. We reran our model multiple times, varying different constants to determine their effect on power consumption. We noted when we increased the AC efficiency, we noticed a decrease in overall power consumption. This is logical, as if the efficiency of AC increases, it would take less power to cool the houses. The sensitivity analysis also revealed that if the temperature set point was decreased, the power consumption would increase. These results provide us with insights into future changes for power consumption for Memphis. Due to rises in global temperatures from global warming and increases in the population, the maximum power draw Memphis will experience during a heat wave will most likely increase. While other factors such as zoning changes in Memphis, requiring better insulation and improved air conditioning technology, will help decrease the amount of power draw the city requires, the increase from rising temperatures and population growth will overall cause the power draw to increase. Our model effectively captures the essential physics of heat transfer and building thermodynamics, allowing for a more accurate power consumption due to air conditioning usage. It also helps capture the nonlinear relationship between temperature and power consumption, giving us insights into how different factors such as the age of the dwellings and shade affect the overall power consumption. One weakness is our model simplifies the diverse Memphis housing stock into 4 archetypal dwellings. Another weakness is that our model also fails to consider differences in the thermostat behavior across different dwellings.
For question 3, we were asked to create a neighborhood vulnerability score to equitably allocate resources during heat waves or power grid failures. And in order to do this, we made 2 key assumptions. First, we assume that all houses built within the same decade share the same construction material and therefore offer same levels of insulation. And second, we assume that the result of a vulnerability index review accurate insights into a resource index. Briefly go over a model for problem 3, we chose to conduct a principal component analysis, or PCA. PCA is a commonly used dimension reductionality technique that also has a secondary use case of determining weights. This second use is what we decided for our solution. This is better as inspecting the weight of each variable on each component allows you to quickly identify which original features drive the most variation, making the data more interpretable and meaningful. As for our methodology, we began by implementing our vulnerability factors into a standard data matrix. Then we computed a covariance matrix for a standard data matrix and extracted its eigenvalues and eigenvectors. We then took the absolute value of the eigenvector entries, scaled them by the corresponding eigenvalues, and summed them to form a vulnerability weight vector, which we then multiplied by the standardized data matrix from before. This produces a weighted vulnerability value vector, which we finally then converted into a vulnerability index per location. We then use this vulnerability index and feed it into our list of resource factor and repeated the process again. This resource index is how we determine which neighborhood required the most aid in a heat wave or power grid failure. These were the relevant equations we used, the top one being one for the weight vector, the second for the value vector, and the last one being the equations for how we convert a value vector into an index score.
The factors we chose to determine the vulnerability weight vector are shown above. This second use is what we decided. The factors which affected the vulnerability score the most are indicated by the length of the arrows above, with green being positive and red being negative. The most impactful factors are the number of households built in 2010 or later and homes built in 1950 or earlier. This lines to reason as it's reasonable to assume that recent households are less susceptible to heat waves and older households are more susceptible. These are the factors we chose for the resource weight vector. The most impactful factors are indicated the same as before. It is important to note that this score also took into account our vulnerability score, which is determined from the vulnerability weight vector. This meant that the resource score not only included demographic factors on individuals in different neighborhoods, but also took into account how vulnerable a given neighborhood is during a heat wave. The 2 most impactful factors for this score are median household income and households with no vehicles. As indicated by the direction of the vector above, the more median household income has, the less resources they need. And if they have little to no vehicles, they will have a higher resource score indicating they need more resources. As for our index, our vulnerability scores were scaled from 0 to 100, with 100 being the most vulnerable and 0 being the least. Looking at the results, we can see that vulnerability, East Memphis scores 100, meaning this area likely faces compounding risks like poverty or environmental hazards. Conversely, Roosevelt scoring 9.99 is not vulnerable during heat waves. Our resource scores were scaled from 0 to 100, with 100 needing the least resources and 0 needing the most. For our resource scores, Collieryville/Pipperton with a score of 100 has robust funding or infrastructure, so they will not be needing any additional resources, while South Forum/Washington Heights with a score of roughly 14 may lack critical services. Some strengths of our model are that no prior resource and vulnerability scores are needed, as PCA is built directly from current inputs. Additionally, PCA makes the standardization more objective due to the PCA makes the assessment more objective due to the standardization of data. Some weaknesses of our model are that feature ambiguity, where linear combinations of all the factors make it hard to isolate individual factors. Service level analysis, while scores rank areas, they don't explain why components such as houses created after 2010 correlate with vulnerability. Deeper component breakdowns would improve actionability. To recap what we have previously covered, in Q1, we have the general energy balance equation, which is a differential equation stemming from Newton's laws of cooling. Temperature caused by body heat, temperature caused by ventilation, and temperature change due to the sun and radiation. In Q2, we utilized our peak energy consumption required equation, which was modeled using a simulation. This allows us to model the peak energy consumption required even if the relationship between the variables is nonlinear. Finally, for Q3, we're a principal component analysis, which allowed us to determine weights for each component. We then use this to create both a vulnerability and resource score to assess the risk level of different neighborhoods. We appreciate your time. Thank you for listening to our presentation.
Can you say again, what were your key items that affected things the most when you did the PCA? I couldn't see very well, that one slide. Yeah, maybe, yes, probably vulnerability, I think. Homes built, the dates that homes were built. Yeah, it's mostly that. Is there anything I'm missing? Anyway, what would you say more about this?
The most important ones were homes built in 2010 or later and homes built in 1950 or earlier.
And can you also do the next slide?
Yeah. So for the resource score, the most important were median household income in dollars and households with no vehicles.
Were there any surprises in general? Were there any surprises from any of the results? Sorry, were there any surprises for any of the results that you found through the whole research endeavor?
Most of it was largely intuitive. With the homes, when we were like estimating their affected temperatures due to the heat waves, we saw that like a lot of the temperatures were expected kind of. In apartments, you would see like higher temperatures because they aren't really an isolated unit. Whereas like older buildings would have a lot more vulnerability as well due to like poor insulation. Yeah.
I got a little confused about where these vulnerability score weights came from. Like what part of the data incorporated heat waves? Like if I had said, is this neighborhood vulnerable to a traffic jam or is this neighborhood vulnerable to a sharp increase in home prices? Would your method here have output different vulnerability scores?
Could you rephrase that last part? I'm so sorry.
Like I think I'm missing. I know you did PCA, but it seems like you did it on data that was data about the neighborhoods. But I was missing where the data on heat, like the information about the fact that we care about heat waves came in. Like if I had asked you to give a vulnerability score to what neighborhood is most vulnerable to have a spike in home prices, I would think I would get different neighborhoods out, but I'm not sure how that would change the output of the model here.
Yeah, Billy, go back a slide. So these factors were what we used in question 1 to determine the temperature. A lot of these were similar. So what we did was we got the eigenvectors and using PCA, we basically got it.
Okay, so the insulation is important to determining the internal temperature of a house, as we showed in question 1, right? And so these homes with built in different years, you could assume that they would have different levels of insulation from those different years, right? And then you also see the proportion of developed or open space in a neighborhood. That open space will help decrease the overall temperature in the neighborhood if it's populated by green space or by other things like such as that.
So I guess I agree that these look reasonable afterwards, right? Like I agree that like insulation affects heat waves and the proportion of developed open space does, but it seems like the methodology used to get these scores didn't know that the problem was about heat waves. If it had been about traffic jams in something that insulation doesn't have an impact on, it seems like you would have gotten the same scores. Or maybe I misunderstood the methodology a little bit. Yeah.
We used the provided data given from you guys for the vulnerabilities, and we.
Oh, you use the.
Yeah, so these data were the same ones we used in the question 1 that are provided. All of these were like already provided to us. And to your point,
you mean this environmental vulnerability? What provided data exactly?
The one provided by like the Envy challenge, which we use these to like the different as like statistics about like the homes and the insulation. And I guess to your point about like using these factors for traffic, yes, we will get the same score. But if you're considering about determining a traffic score, we don't think it will be logical to have information about homes necessarily. And in that case, you'll more use factors are already related to traffic and not that already related somehow and not more about the homes.
Okay. Okay, great. Makes sense. Thank you.
I had a question about, in the paper itself, you talk about your power due to conduction incorporates the solar power.
Yeah.
I was wondering if you could talk a little bit about that, how you
So
think about that.
essentially, for Newton's law of cooling, we calculate like the amount of outdoor temperature, like how that affects the indoor temperature. And part of that considers what we interpret it as is the literal solar radiation. So like the area and the literal like sunniness that the house is exposed to. Make sense?
So how's that going to be incorporated in this term that is the differences in the temperatures?
So we have this TSA variable, which is like solar radiation as well as the outdoor temperature. So we would calculate the effect of the shadiness within the solar temperature, the TSA variable. That clarify it? Can I like explain it more or?
Well, in the paper itself, you said that, okay, I'm misunderstanding then when, okay.
Does that clarify anything?
Yes, yeah, yes, thank you.
My question is about part two. You mentioned electrical consumption patterns in Memphis will likely have changed. Climate change, population growth, technological advances. How could you modify your model to adjust to those changes?
Okay, so to adjust our model for temperature changes, we would just simply adjust the heat wave data that we were training it on, that we used to calculate the overall power. If we wanted to change the population, we could probably find the ratio of population to number of dwellings, and then we could then scale our simulation to increase the number of dwellings that we're calculating. And I'm sorry, what were the other ones you asked?
Technological evolution, like electrical vehicles, for example, energy efficient appliances.
Okay, so for that, we could simply just change, we would modify the coefficient of performance for AC units, because that could, as AC unit technology increases, you would expect the amount of energy required for it to cool the house down would decrease, which would then bring the overall power required down. Does that answer your question?
Yeah, absolutely. Thank you.
Great. Thanks, guys. Yeah, if you want to do any thank yous for anyone, you can do it now.
I would love to do some thank yous. First, I would love to say thank you to Jane Street for hosting such an amazing event. And thank you to SciAm for giving us the opportunity to present our solution to everyone here. My team and I are incredibly grateful to all our friends and family who have been supporting us, and particular thanks to the Flint Hill Math and Science departments for really making this possible. And last but most certainly not least, the biggest thanks to our coach, the wonderful Miss Van Lieshout, for spending so much time in her last year before retirement, helping us do what we couldn't have done without her. And thank you to Mr. Weeks for being here with us and making multivariable calculus really fun.
solution. And building applied math skills means that we're building a generation of people who know how to do that. And that is very influenced by M3. Those are the types of thinkers that we need to just build a better world.
What do you think? Pretty good. Ah, thank you. It would be helpful if the teams would move up. If you guys have a chance, you want to fill in the front row, I would love it. Thanks. As you're doing that, one of our staff members who played a large role in the production of the video asked me how I managed to find these 3 amazing past participants to be in this video. And he was like, how did you find these 3 in particular incredible people? And I said, it wouldn't matter. I could pick any of our finalists and it would look like that because it's so good. Sorry. And I'm so excited that you all will be joining them. You're part of the team now. That's good. This year, we asked teams to address a problem that we call the hot button issue, staying cool as the world heats up, which addressed issues around heat waves and potential for associated strain on the power grid. If you had a chance to see just one of the presentations, I was thinking of 18111's presentation. They had a whole slew of headlines about how big of a deal this is, right? And so big, huge issue that I'm gonna guess that most of these teams hadn't really thought of, right? Before you downloaded that question, you weren't like, it's a big issue, facing the world, but it's a big issue and it's one that's sort of under the radar. And so we're so excited that we had a chance to have you really propose some good solutions and think about what this looks like moving forward. So that's exciting stuff. And our guest that was here earlier this morning speaking to you talks about how this is a current area of research for her, right? So there are people who are trying to solve the same problem that you all worked on, and that's really amazing. But this means that for you all, when you downloaded the question, you had to start from ground zero, learning about the problem, diving into the data that we provided, filling in the gaps in the data, because we certainly didn't give you everything that you might need, figuring out how to use math and data to help provide insight into solutions for these. The finalists that are here today excelled both in their modeling and in their exposition, and they did it all in 14 hours, and they are truly exceptional. So I want to thank all of you right now. Thank you. 794 teams submitted solutions, and we are here in this room with 9 teams, so everyone here is exceptional. I would like now to introduce the Chief Executive Officer of Society for Industrial and Applied Mathematics, who earned her PhD in mathematics and scientific computing from University of Michigan. Please join me in welcoming Dr. Suzanne Weeks.
Thanks very much, everyone. Let's see. This is the device for me to avoid saying, can you hear me? Because there's an actual device that's been invented called a microphone. So that's what I'll use. Good. So I want to add my congratulations, of course, to you all. As Dr. Bliss has just said, you're 9 teams out of just under 800. So I'm going to ask you to engage with me by applauding a lot. So I would like you all to give yourselves a round of applause. Yeah. And of course, so not just congratulations to the students, but congratulations to the teachers, the coaches, and not just people here, everyone who participated in the M3 challenge. The teachers, the coaches, and the parents who, and the students, you took up and met the M3 challenge. And what do I mean by meeting the M3 challenge, right? It's clicking on that button, knowing that once you click, there's a clock that started, right? It's gonna run out in 14 hours. Meeting the challenge means being creative, being courageous. I think it takes a lot. How many of you think it takes a lot of courage to do this, to get out there? Nobody, just me, right? To do this, venturing forth, knowing that there is not a solution in the back of some book that you can just look up to check if you're going on the right path, right? You have to be courageous. You got to be creative. You have to work with each other. How many tears were there in this room? Did anyone? No tears? Good. How many arguments? Any team arguments at all? All right. Don't lie. Today's not the day to lie, right? But you figured it out. And I don't know if we've expressed this explicitly today yet, but I want to say how impressive it is, your communication skills. So within 14 hours, not just exploring and looking at a problem that you didn't start the 14 hours knowing what this problem is. And you did all this work, all this research, all this analysis, and then you wrote it up legibly in coherent sentences with good punctuation and their tables and all these things. And then of course you had some time once you made the finals to have these beautiful presentations. So I really want to congratulate you because it's been absolutely impressive. So I want to, of course, I know all of you have, thank you so much to Jane Street for hosting us here and giving us these wonderful meals and all these treats and all these, in a wonderful room. So I really appreciate it. And I hope you're all aspiring in your various professions and careers, and consider Jane Street when you go forward, when you're finished with your education. Maybe this is a place you can intern, right? This is a time you just, share your LinkedIn contacts, right? And the biggest thank you, right? Maybe it's the second or third biggest thank you, but definitely to MathWorks, right? Where's Tanya? Sonia, thank you, Tanya. It's very special. We could not do this without MathWorks. It takes support, it takes a partnership, it takes funding to run this, right? It takes a lot of effort, staff time, judges time, everything, your time. So thank you to MathWorks for continuing to work with SIAM and for trusting SIAM with the MathWorks Math Modeling Challenge that bears the name of the company. So let's all thank Math. Yeah, so yeah. MathWorks and SIAM have a long history even beyond this challenge. So I think we make a good partnership and we can continue this for many more years going forward. Thank you to our fearless leader, SIAM's Karen Bliss, for leading this whole operation. So thank you, Karen. So I'm gonna say, I know you've heard about SIAM a bit in remarks today, but I'm the CEO, so I have to tell you by my own mandate to myself, say a little bit more about SIAM. So just bear with me. But SIAM, who are we? We are an international organization, right? A professional society, and we're a publishing house. We're headquartered in the US. Actually, our headquarters is in Philadelphia, but we serve and work with students and professionals from all over the world, right? People who are interested in applied mathematics and computational science and data science, and those are our people, right? It's a home and it's a community, right? We don't do our work. You all just showed that, right? Could you have done all this stuff by yourself? Yes. Would it have been as much fun? Maybe not, right? But the team work is great and the community is what we provide at SIAM. And we're mission driven. We have a mission to advance the application of applied math and computational science and data science to engineering, industry, science, and society, and to promote research that will lead to new and effective mathematical and computational methods and techniques. We bring people together via our conferences. We bring people together from the media that we produce, right? We publish the best journals in applied math and computational sciences in the world. We publish books, our SIAM News, guys will be profiled in a SIAM news article, so look out for that in our monthly newsletters, right? So those are the things we do. We also advocate and serve as the voice for applied mathematicians and computational scientists, in this world, right? We function as a source of information for public and private agencies. You don't want biologists, nothing against biologists, but you don't need biologists speaking for applied mathematicians. You don't need, there has to be a collective voice, and SIAM and professional societies do that, right? You don't exist. Try not to exist in the world by yourself. A community is helpful. As I said before, we're global. We have 13,000 official members and tens of thousands more who engage with us by submitting research articles for our publications or attending our conferences. And of course, as you well know, we run exciting programs to foster the development of our young people, and you're our people now, right? So you're our people. I hope you've learned that math is important for making decisions and for making choices, for analyzing, for understanding, and for predicting, right? Math is important for understanding our world. And there's really, if you look at all the problems over the years we've done, right? There's almost no endeavor, right, you can think of that does not involve an engaged mathematical sciences, right? Or statistics, or at this point, data analysis. And of course, for modeling, you're using the modeling to understand the world. Mathematics is absolutely intrinsic to our lives and absolutely fundamental. So anyway, M3 channel challenge. M3 challenge, right, was conceived as a program of SIAM in 2005. You've just seen our 20th anniversary video. The first context took place in March 2006. And I think you've met her briefly before, but let's all turn and say thank you again to Michelle Montgomery, who got this program going at SIAM 20 years ago. So thank you, Michelle. So very quickly, let me say, in those 20 years, we've had over 14,300 teams participate in M3. They've hunkered down and met the challenge. That's 65,000 students, including a set of twins in 2008, including a set of twins in 2025. Where are our twins? Or half of twins, is that right? Okay, good. So we met our twins today. More than 110 judges have worked to assess these papers, right? This year, let me go back. Over 5,000 individual math teachers have coached teams. And from a previous sponsorship to now with MathWorks, we've been able to give over $2 million in scholarship and prizes. That's a lot of money. That's a lot of money, right? To support our students. This year, we've done just under 200 teams submitted papers for review. More than 110 judges assessed the papers, with 13 of those specifically focused on the technical computing aspect, right? That's a lot. And with regards to technical computing, we've had about 44% more papers getting submitted for technical computing assessment than we did last year, and 5 times as many as we did when we started the technical computing aspect in 2018. That's a lot. That's a lot of computing. And that's great. It's so fundamental. So thank you, everyone, for engaging and doing so well. Anyway, I should stop because there is a schedule. So let me do this. I'd like to welcome Tanya Kuruvilla from MathWorks. She'll be presenting the Outstanding Communication Award, followed by the Technical Computing Awards. And thank you again, and congratulations to everyone in here.
Hi, everyone. Awesome job today. It was so great to watch all of your presentations. And thank you for sharing your solutions on how you approach this year's problem statement. It was very fascinating and very engaging. So I'm here to present a couple of awards, and we're going to get started with the M3 Outstanding Communication of Results Award. So MathWorks is struck by the extraordinary clarity, presence, and polish of students talking about their solutions at the final event. In 2019, an award was created for what the audience saw and experienced today. Excellent communication and grace under pressure. Though all teams demonstrated excellence, we picked one team that stood out the most. The M3 Challenge Outstanding Communication of Results Award goes to the best overall presentation of the day and adds $500 to your overall scholarship award amount. And this year, the award goes to Haberdashers Boys School. And now on to the M3 Technical Computing Awards. And there are 3 awards for technical computing for outstanding use of computer programming in a solution for the challenge problem. 13 judges specifically assessed code submissions from more than 494 teams over 2 intense rounds of scrutiny to look for teams that best advance their model using computing. Now for the winners of these awards. In 3rd place, here's what the judges said about this submission. This team hand-coded a detailed model for part 1 to predict temperature change over time. They effectively used technical computing to produce informative plots involving several time series, each corresponding to a different choice of model parameters. In part 2, they continued the effective use of plotting, where they used built-in functions for time series fitting. Overall, the solution was a nice read and had exemplary use of coding for simulation. With a team scholarship of $1,000 overlaid on any other distinction, the Technical Computing 3rd place award goes to Trinity Preparatory School. In 2nd place, judges had this to say about the paper. Like many teams for part 1, these students modeled the change in temperature over time and hand-coded a simulation to determine how temperature changed throughout the day. What made the solution stand out was its effectiveness at showcasing the potential of technical computing by incorporating many additional variables to the model that would have been difficult without a code-based approach. The team also used effective code in part 2, and their writing led to an overall very strong paper. With a team prize of $2,000 overlaid on any other distinction, the Technical Computing runner-up award goes to Haberdashers Boys School. And now for 1st place. Judges made the following comments about this paper. This team leveraged a mix of hand-coded models and built-in libraries. What stood out most was the use of technical computing in part 3. For that problem, the team imported data to approximate the number of power substations within each neighborhood, which factored into their vulnerability score. They proposed a simple but effective algorithm to place cooling centers throughout Memphis to maximize impact. We did not see any other teams use mapping libraries so effectively. So with a team scholarship award of $3,000 overlaid on any other distinction, the technical computing winner award goes to Winchester College. And now Dr. Karen Bliss will present the overall M3 Challenge Scholarship Awards.
Before we announce team awards, I want to take a moment to acknowledge the contribution of M3 Challenge team coaches for inspiring students to study and pursue careers in applied math, data and computational science, and technical computing. So thank you again to the coaches that are here. And I want to remind everybody one more time, 794 teams actually rose to the challenge and submitted a solution. And we have the top 9 teams in the room. That's less than 1.5% of the field. They're here today. So we're proud of all of you. We're going to be announcing third place, runner-up, and first place. Okay. The finalist awards honor the top 6 teams for overall outstanding mathematical approaches to the 3 main prompts in the challenge problem. Teams were asked to create mathematical models, justify assumptions, define parameters, describe their process, analyze effects of change, and describe results. More than 120 math and computational professionals assessed the 794 submissions over 3 rounds of increasingly intense scrutiny to find creative, thoughtful, well-justified, and reasonable solutions. We've arrived at the 3 papers that are going to be awarded the overall third place runner-up and champion titles. So when I announce these teams again, come on up to the podium to accept your awards. Here we go. For third place, here are some of the comments that judges made about this paper. The first differential equation model is comprehensive, incorporating conduction, radiation, ventilation, and internal heat sources. The second model of multivariate regression is robust with backward selection and multi-collinearity analysis. The third model is practical with normalized factors for actionable policy recommendations. Overall, the paper successfully responds to all 3 parts of the challenge question. The models were thoughtfully constructed and modeling choices were explained well. With a team scholarship award of $10,000, the award of M3 Challenge third place goes to St. John's School, team 17524 from Houston, Texas. For runner-up, here is what judges said about this solution. The team provided a very good executive summary highlighting their models and demonstrating the results they derived. The paper has a well-defined structure for model setup and analysis, clearly defining the models and how sensitive they are. It is exceptionally well-written and includes nicely presented plots. With a team scholarship award of $15,000, the award of M3 Challenge runner-up goes to North Carolina School of Science and Mathematics, 17928 from Durham, North Carolina. And now for the M3 Challenge champions. Judges had this to say about this team's paper. The executive summary was perfect. The team did a good job stating in part 1 and stating and justifying your model throughout. The use of charts and images helped explain the models. The team presented good critical and analytical thinking in each part of the challenge, and the overall solution was very strong. With a team scholarship award of $20,000, the award of M3 Challenge Champion goes to William Mason High School, team 18111, Mason, Ohio.